Good evening, everyone. It's a great pleasure to welcome you all to our online faculty development program, Day 3, on Advances in AI, Applications and Ethical Dimensions in Intelligent Systems and Digital Security, organized by Department of Computer Science, Nirmala College, Muatupura, Autonomous. I'm Vidula Thomas, and I'm honored to serve as your host today. A warm welcome to our esteemed guest speakers who will be sharing their expertise with us. Let's take full advantage of this opportunity to learn and grow together. It gives me immense pleasure to see participants joining from different places, bringing together a diverse pool of knowledge and experiences. Today, we'll be having two sessions. First session is on generative adversarial networks, concepts and applications by Dr. Mercy Paul Selwyn. And second session is on AI-driven intelligent connectivity for cyber-physical systems in next-gen networks by Dr. Rajesh GK. Before we begin, I request all participants to kindly ensure that you have signed in with your correct names for attendance purposes. Please keep your microphones muted during the sessions unless you have any query. And feel free to use the chat box for queries or interactions. Once again, welcome to the FDP. With that, I would like to invite Ms. Priya Peter, Assistant Professor, Department of Computer Science, Nirmala College, Muatupura, Autonomous, to come forward and to introduce our resource person.
Good evening, everyone. We are truly honored to have with us Dr. Mercy Paul Selwyn, Professor in the Department of Computer Science and Engineering at Satyabama Institute of Science and Technology, Chennai. Dr. Mercy has been serving the institution with dedication for over 17 years, contributing immensely to both teaching and research. She holds her master's degree in engineering from St. Joseph's College of Engineering, Chennai, and earned her PhD in the specialized field of web mining and machine learning from Satyabama Institute of Science and Technology. Her remarkable academic journey is reflected through more than 80 publications in reputed national and international journals and conferences. She has also been granted a patent, highlighting her innovative spirit, and successfully completed a DST TIDE funded project worth 25 lakhs, demonstrating her excellence in research and project execution. Her core research interests span across artificial intelligence, machine learning, deep learning, and data science, where she actively mentors students and scholars, nurturing the next generation of researchers. With her vast expertise and significant contributions, Dr. Mercy continues to be a driving force in advancing computer science education and research. On behalf of everyone present here, I extend a warm welcome to you, ma'am. We are delighted to have you with us today, and we look forward to gaining valuable insights from your sessions. Let us warmly welcome Dr. Mercy Paul Selwyn to lead us into today's session. Over to you, ma'am.
Thank you so much, ma'am. Thank you so much for the warm welcome. And let us start without any delay. I'm sharing the screen, ma'am. Ma'am, is the screen visible, ma'am?
Yes, ma'am.
Okay. Okay. Good evening, one and all present here. I'm Dr. Mercy Paul Selwyn, professor from Satyabama University. And today we are going to see GAN, Generative Adversarial Network, right? Okay. So what is GAN? As a name explores, it is a generative AI. It is a part of Gen AI. So it is Generative Adversarial Network. So what do you mean by adversary? Opponent. Okay. So as name explores, we have two neural network model here, and it is a type of deep learning model. It is introduced by a researcher called Ian Goodfellow in the year of 2014. Okay, so as you all know, this is your deep learning model. So you'll have input layers, you'll have so many hidden layers in between, and you'll also have output layers. So you'll map whatever the input is given with the output, and we do not know exactly what has happened during the training, and we all will we are going to see what is going to happen there. Okay. So as an introductory one, this is a generative adversarial network, and it has got two neural networks. It is like a gaming scenario. Like we all know like what is Minimax algorithm. So it is such an algorithm. It competes with one another. We have two model as a core. One is called as generator model. The other one is called as discriminator model. Here, both of the models are trying to compete with each other so that as an outcome, we are going to have such an amazing output, right? Okay. What is the main motivation and what is the main intention to develop this particular model, right? It is a powerful generative model. As we all know, what is generative model? It creates something. It creates, right? So it can learn to create new data, such a realistic data, rather than just qualify or just to predict. And when we were as students or UG students, or sorry, like school students, we had a traditional approach, right? What is a traditional approach? We are giving the input and we are writing the program, may it be Fibonacci series or may it be factorial generation, or it may be sum of two numbers, whatever it may be. We are giving input to the system and we are giving the algorithm or program to the system. Okay, and we are expecting the system to generate the output, right? This is what we are expecting through traditional programming style. And days go by, we are shifting to machine learning concept where we have enough input and output in the form of data set, right? So we are in a social media era, like Twitters are generating so many bytes of data. Facebook is generating more than enough amount of data, and all social media platforms are generating so much of data. So we have enough data now, right? So data set we have what could be the input and what could be the output. Say, for example, we are taking rainfall data. We know what and all would be the features, X parameters, and what could be the output. Say, for example, what could be the humidity on a particular day, what could be the temperature over the particular day. These are all X features. And we also know whether we had a rainfall on a particular day or we did not have a rainfall on a particular day as Y parameter, right? So we have enough data set now. We have input as well as output. This customer is going to Nilgiris or some supermarket, and these are the type of customers, they are buying these type of products. So we have enough data. We have input as well as output. Yes or no, right? So I want this session to be very interactive session. So please know, you have to, every word is important, every slide is important, right? So I want your full attention here. So before we had traditional approach, and now we have machine learning approach, right? Machine learning is all about, we know we are enough providers of
Ma'am,
giving.
sorry to interrupt.
Yes,
Ma'am,
ma'am.
can you play the slideshow?
I'm sorry, ma'am. I'm sorry. Yes, ma'am. Is it fine, ma'am? Hello? Ma'am, is it
No,
fine?
ma'am.
No, ma'am.
No, no, ma'am.
No, ma'am. No.
1 minute, ma'am. One minute. Ma'am, is it okay? Ma'am, is it
No.
okay?
No,
Not-
ma'am.
No. 1 minute, ma'am. Now, ma'am?
No, ma'am. I'm sorry. It's not okay.
Sorry, ma'am.
Ma'am, just press F5 or slideshow
Yes, ma'am.
F5.
No, for me it is working. That's what, ma'am. For
Okay,
me
okay,
it is working. Yeah, for me it's working. Ma'am, can you now as a full screen?
Not yet, ma'am.
Not it. For me it's working. And I do not know what has happened. For me, it's going, it's just showing full screen. At least slides are moving, ma'am.
Ma'am, I think you have shared only the window. We have to share the entire screen.
1 minute, ma'am. Let me check. Is it okay, ma'am?
Now it's okay, ma'am. Okay. Okay.
Sorry,
Yes,
ma'am.
ma'am.
From my side, ma'am. From my side, I'm sorry. Like I am in a little bit tensed mode today. Okay, ma'am. So will it be fine now? Okay. So where I left. Okay. Where I left, ma'am, this slide, right? Okay. So we are so what I'm talking about is traditional approach, and traditional approach is all about like we are giving input and we are giving program or algorithm, and we are expecting the system to generate output. And as days go by, as I told you, we are we have been entered into a machine learning era, and where we have more than enough huge amount of data we have. So we have data, we have input as well as output. Now we expect system to generate the program or algorithm in turn. We are not giving program to the system. We only give, now in turn we are giving input and output to the system, and we are expecting system to generate program or algorithm. That is nothing but the program and algorithm is nothing but the relationship between input and output, right? So what is the input in the data set and what is its appropriate output? I want to get the mapping from the system. So system in turn, I expect to just go through the data set, and it has to get the pattern or underlying function over the data. So this is what is happening in machine learning, right? Even in deep learning. So we are giving data set in the form of input and output, and in turn, deep learning algorithm will try to squeeze out the pattern, underlying pattern between input and output, right? And it will give you the program. And that particular program, we call it as a function. Underlying pattern in terms of mathematical function it will try to give. So that we are calling as a model. So we are telling model. So what is model? This particular underlying pattern recognition, we call it as a model. So once particular model is squeezed or model is identified, using that particular model, or colloquially or mathematically we speak, it is a function. It's a mathematical function. By using mathematical function, any input in future if you give, by using the function, we'll try to get the output. Right? So this is what happening in machine learning era. Now machine learning, we as a subset, we have deep learning algorithm, right? And moving from deep learning algorithm, now we are going to, we are having Gen I right now, and this Gen I is creating new data, right? It is not just there to classify or to predict the data. Here, you can learn to create the data out of some garbage data. It will be able to create some data. That's what we are going to see in the upcoming slide. The difference between the classification and like supervised learning, unsupervised learning, and Gen AI. So as of now, the main intention or motivation of this particular powerful generative model is to learn how to create new data, how to create even realistic data other than classification or prediction. So we had enough earlier generative models, but while comparing this to the GAN, that is generative adversarial learning, comparing that, it has its own limitations. Okay, it doesn't create high quality, sharp, realistic output, and the approach is also exactly same with the GAN model. And this good fellow wanted a model, okay, and he wanted to exactly learn the distribution of data, okay, so that by using that particular distribution, he'll be able to create some other typical data similar, not exactly similar, but still, okay, based on the distribution of data, he is going to create some other new data, right? So this is the intent or motivation of this powerful generative model. Okay, look at the pictures. Okay, these are all generated images which are not real. Okay, these are the images which are created, which are generated by the GAN model, generative adversarial network, where by using generator and discriminator, right? Okay, and these are the portraits were made by artificial intelligence. That is GAN approach here. None of the people are really exist on the earth, right? So this is a power of GAN, right? So the data can be anything. It can be an image data, it can be a text data, or it can be some audio data, right? Using GAN. GAN is just a framework having two network model. One is generator, the other one is discriminator. And by using these competing networks, we can generate any type of data. So what could be the input data? Accordingly, you'll get the output data. And how do you figure out, right? Okay, this is a parse GAN we have. Okay, what is the key idea behind GANs? So instead of explicitly modeling data distribution, we are introducing adversarial training, right? So I hope you know what is all about data distribution. So what is data distribution? Particular data set, how data is being distributed, right? How data is being distributed. Just like no, it is not exactly a histogram. I can tell, in order to make you understand what is data distribution. It is something like histogram. You have to learn about the data, how the data is being distributed, whether it is normal distribution or something else. Okay. So what is histogram after all? You have a data set. Say, for example, we are all faculties, and we are giving marks for our course to students. And when we look into the marks, you can try to figure out the range, right? So 1 to 10. How many students have secured? 11 to 20 marks, how many students have secured? It's a distribution, it's a frequency distribution. So how many students have got, right? So when you look at it, if it is normal distribution, all data would be towards the mean. What do you mean by that? So many students would have secured, if the average of your students' mark for a particular class is 70 marks, then all the students, most of the students' marks will be towards mean. That means students would have got 73, 69, okay, 72, 65, something like closer to mean. Some outliers would be there, which is far away from the mean value. We call those as outliers, right? So this is called data distribution. It is not exactly histogram. Here we call it as a probability distribution. How probably, or what is the most probability of occurring this particular data over there? Something like that. We call it as data distribution. So instead of explicitly modeling data distribution, we have a competing network model. One is known as generator model, which learns to create realistic data. The other model is called as discriminator model, which learns to detect the fake data. So whatever generator is generating, okay, it should be realistic, and it should be, it will try to fool the discriminator, and in turn, discriminator should be sharp enough to identify the fake data which is generated by the generator. Okay, so this competing game between the generator and discriminator will give you as an output a realistic one. So this adversarial game pushes the generator to produce some output, and that output will be given as an input to the discriminator along with the real data, and it will train the model. The discriminator will train accordingly, and it will try to detect the fake data based on the generated model. So initial level, whatever the images generator or whatever the data generated by the generator will be considered as fake data. Right? We are going to see how this exactly works. right? And these are the two models of GAN. One is generator, the other one is discriminator. 1 minute. Okay. One is the generator. So generator will take noise vector. Okay, noise vector. We call it as latent space, and we take that data and it will create the fake sample. Okay, and that fake sample and the real data will be given to the discriminator. Okay, and discriminator will train with these data and it will try to figure out what is real data. It will be able to classify what is real data and what is fake data. Okay, so we'll go to the next slide to make it more understandable. So why it is important? It was a breakthrough. This GAN adventure, okay, the GAN, this particular introduction of GAN, okay, the discovery of the invention of GAN, okay, is considered as a breakthrough in unsupervised learning, training without labels, right? We are giving only the input. I mean, we don't have enough Y label. No? We are giving input, like we are giving a data set comprises of X parameters. We don't need Y parameter, right? So this is considered as unsupervised learning, and even in unsupervised learning, this is considered as a breakthrough, right? So it opened the door to creative AI applications. Okay, when you talk about unsupervised learning, like you have clustering as an unsupervised learning that will not create any data. But in case of GAN, still it's an unsupervised learning, but it creates AI applications, right? Such as photorealistic images, art, cloning, audio, or deep fakes. We call deep fakes, right? So text to image generation. What do you mean by deep fake? Can anyone answer? What is deep fake? Can anyone answer what is deep fake? Can you put it in the chat otherwise? What is deep fake? Deep fake is a deep learning model. They are exploiting GAN technology in order to clone audios and video. Say, for example, you can give audio, okay, my audio, for example, and the audio can be taken and you can generate by using GAN, you can give as an outcome as if Trump is speaking, Mr. Donald Trump is speaking, is giving a lecture like this. Okay, you can clone like that. Okay, so for that, Trump's audio could be the way of speaking could be trained, and the content could be given. It is my lecture, and you can figure out something as if Trump is giving the lecture. That is called as deep fake. Okay, so deep fake is done by using GAN. Text to image generation. So many applications are there in terms of GAN. Okay, this good fellow himself described GANs as a way to let a model imagine data. So model itself is imagining data. We do not know what data is going to get as an outcome, right? Okay. So this is a breakthrough in unsupervised learning. How? Right? So in what way AI is different from supervised learning and unsupervised learning? So what is the aim of supervised learning? As I told you already, we are providing data set where we have X parameters and Y parameters. Say, for example, you have a fruit data set where X parameters is all about the color of a fruit, the weight of a fruit, taste of a fruit, something like that. And Y label could be mango, orange, banana, something like that. So you have X parameter, you have Y parameter, right? So each example has a label, right? What do you mean by label? Under Y parameter, I specify that as mango. That is a label. Banana, that is a label. So across you have X parameter, X1, X2. Color is X1, weight is X2, taste is X3, something like that. You have X parameters and you will always have one Y parameter, which is a label if it is a categorical data, or you will have some real values, numbers, if it is a regression. Okay, so you know what is the difference between classification and regression. Today we'll have a rainfall or not is known as classification. How much rainfall we'll have is always known as regression. Okay, so this is something like, you're going to predict output. Okay, so it will try to, in the supervised learning, we are trying to learn the underlying pattern in order to predict the output. So we are trying to learn the underlying function. By using that function, any unknown x value is given with the pattern we got it, or with a revealed pattern, we apply x and we are going to predict the y value. So supervised learning is all about predicting output, okay, based on a model, right? So examples are linear regression, logistic regression, random forest, CNN, so and so. Okay, so what is the intuitive part here? Teacher gives you a question and answer. You learn to predict the answer for the new question, right? Understood? Okay. So what is all about supervised learning? Supervised learning, you will not have y parameter. Though you have y parameter in the data set, you are not going to consider y parameter. It's all about x parameters alone. So what can be done? Clustering can be done, dimensionality reductions can be done, something like that. So you focus only on x parameters, and based on some attribute, you're going to group the data, right? So you're going to learn the relationship, structure, or distribution in the data. So even here, you're not going to create any data like GAN. Okay, so you're going to cluster, or you're going to reduce the dimension, something like that. Okay. Understood? So, no, Gen AI is something different from supervised learning and unsupervised learning. In Gen AI, we are going to generate new data. Okay, we are not going to just predict. We are not just cluster or group something. Or this is all about creating new data, right? So, data can be a labeled data or unlabeled data. But our focus is on learning the underlying data, right? Okay. So what are the task types? Image generation, text generation, music, code, videos, and all. Okay. So the key idea, please listen carefully. The key idea is to learn P of data, the probability of data of X sample, okay, into the probability distribution. Okay, we'll move on to the next slide in order to explain. The example algorithms are, 1 minute, I'll try to tell the people not to be quiet. 1 minute. Dennis, I'm sorry. Is it clear?
Yes, ma'am, it's clear.
Sorry,
Okay.
sorry. Yeah.
Yeah, it's okay, ma'am, it's okay.
Okay. Okay. So, right. So this is the difference between supervised learning, unsupervised learning, and generative AI learning. So labels are given for supervised learning. For unsupervised learning, we don't provide labels. We consider only the X value. And generative AI, probably we may have or we may not have. Okay, that is not a considerative part here. And goal is to predict output. In unsupervised learning, we are going to find the patterns alone. And in Gen AI, we are going to generate the realistic data, right? And example for supervisors, whenever you give an image, you're going to pick out the label, whether it's a mango or banana, something else. And in supervised learning, we are going to group images, right? Gen AI, we are going to create new images, right? Okay. So in short, this researcher introduced GANs to enable machines to generate new data. And we have two components. One is called generator, the other one is called discriminator. And to overcome the weaknesses of earlier generative models, like VAE, something like that. Okay. So how exactly GAN works? This generator takes random noise. Okay. It takes a random noise as an input and it generates the data. It should have something to generate some data. So this generator takes some random noise. Okay. So we are going to see in upcoming slide what is a random noise and all. As of now, you try to understand generator model will take random noise as an input and it will generate some data, right? and the discriminator model will receive the data and it is labeled as fake data. So whatever generator is generating initially, those are considered as fake data, and this discriminator will receive fake data from the generator and the real data from the data set. Okay, data sets, and combinedly we are giving along with labels. Okay, fake data is known as fake data, the real data is known as real data, and this combination will be given to the discriminator, and it tries to train based on the data set given, classifies real as real, fake as fake. Okay, so both networks are getting trained simultaneously, right? So what is the core intent here? The generator improves, okay, its efficiency by trying to fool the discriminator, and in the vice versa, the discriminator improves by getting better by spotting a fake data. So they are competitors. Okay, generator will try to fool discriminator. In turn, discriminator will not be fooled or will not be getting fooled by the generator, right? So this will keep continuing till generator produces a very good data where it could not be labeled as fake data. Okay, so at one point what will happen, discriminator will try to get fooled, okay, by the generator, okay, with the generator data, right? So that much realistic data will be generated by generator as time goes by. Okay, by the point we will stop. Okay, so what is the analogy of this particular GAN approach? Think of a counterfeiter was police officer, the thief was police officer. Thief makes fake currency, and the police officer will try to figure out the fake notes. Okay, like a Turing machine, right? So over time, both will improve their skills, and eventually, okay, this particular thief will generate the data as if it looks very real, so that the discriminator will not be able to figure out. So this is the GAN approach. Okay, now we are going to see shortly, what are the applications of GAN, right? Okay, so the applications of GANs are image generation. Okay, so creating realistic photos. Now, we are seeing in Android phone and iPhone and all, we are taking a photo and we put lots of glitter and we put lots of gimmicks and all over there in order to make it very attractive one. So behind, we have GAN. So image to image translation. So we are converting sketches to photos. Black and white images are given, and that will be converted into color photo. When we give a photo which is a photo of something took at daytime, and that could be converted into a photo such as it could be taken as nighttime, right? So those image to image translation is an application of GAN, right? And super resolution, you can increase the resolution so that you will be able to increase the image quality. So that can be done by using GAN, right? And text to image. That's what I'm telling you. It's all about AI, generating images from text. So I can tell, I want a ball or I want an apple, something like that. By using the text, it will be able to generate the image, right? So images from text description. This is also an application of GAN. And data augmentation is special, okay, one we are using as a researcher, we are all using, right? So what is data augmentation? Sometimes we don't get real data, enough amount of real data. So medical imaging and all, when we do the research, we don't get enough amount of data. Okay, we go to hospitals, we collect data, we go to some challenged people, hospitals and all, like there we are collecting data, but enough data we are not going to, sometimes we may not get. So what we can do, we can augment the data. Okay, so something like having the data at hand, you can produce realistic synthetic data in order to give enough data to the deep learning model to get trained, because deep learning model, we need enough amount of data. We cannot give scar amount of data, no, we cannot give. So in that case, a huge amount of data, enough amount of data, surplus amount of data should be given to the model in order to get trained. So in that case, you can use data augmentation technique, okay, as a pre-processing technique, right? Okay, so yes, see the picture, you'll have a picture like this that will be converted into this right hand side picture. Okay, you can apply color or something else. Okay, see the shades as if some sunlight over there, and the tree is not something like that. No, you can change the picture into some other with high resolution and with some filters. Okay, you can have. Okay, so it obviously or eventually it will improve the quality and it will restore the color as well. Okay, you can have some more features, and you can restore the colors, right? And frame rate optimization, you can have the temporal interpolation for these viewing experiences and all, right? Okay, so video prediction and generation. So you can have a pattern recognition and self-driving car. Okay, you can tell them to act proactively to the dynamic situations. There you can apply GAN technique, and you can generate some realistic images, videos, audio, and so on. And text to speech and audio synthesis. Okay, where we are going to use GAN technique, where you'll have cloning, as I told you, as if I'm talking. All right, you can give my voice and you can manipulate as Mr. Trump, Donald Trump is talking or giving a lecture or something else, right? You can use for in-house projects as well. This technique can be used for in-house projects as well, right? And for educational applications, you can use this, right? So audio lectures, making learning more accessible. Okay, so in many fields we can use this GAN technique. 3D object and shape generation. In virtual reality, we can use GAN. So many fields. In gaming aspects, we can apply GAN technology, right? In manufacturing, in advertisement. Seriously, in advertisement, it plays a vital role. No, instead of now procuring celebrities, say for example, you can go approach celebrities that will cost much. Okay, so instead of celebrities, you can generate 3D videos as if some celebrity is there, but ethically it is not correct. But still, you can have some other good looking like heroes, something, some images you can produce, right? That will be useful for marketing field in order to boost the sales. So industry impact from healthcare to fashion. So in fashion also, you can exploit this technology to as if you're wearing the spectacles, whether it is matches to you and all. So those are all you can use GAN technology, right? In healthcare, so many fields we are applying GAN technique, right? So ethically, it must be good. That's what I say. No, you cannot exploit. No, you cannot exploit. Sometimes these fakes people are exploiting as if they are spreading negative some points, and they are manipulating as if a well-known celebrity or politician or giving the lecture or giving some points. So ethically, it should not be good. So ethical considerations must be taken care in this GAN, right? Multimodal. What is multimodal? The data comprises of text data, image data, audio data, video data. So many types of data can be integrated as a data set, and you can go create a task. Okay, so beyond, okay, 2025 and beyond, okay, you can have so many things with GAN. So future is all about Gen AI, right? Yes. Now, mathematically, we have seen the applications overall. Now, please be attentive. We are going to see the mathematical part of GAN. So as I told you already, GAN consists of two models. One is called generator model, which is represented as G. And the parameters are Z and theta G. Z is nothing but random noise. This particular Z, okay, we call it as noise vector or the random noise. And theta is nothing but the weight we are going to train. After training, we'll get the tuned weight. That exactly those weights we call as model. For example, in linear regression, we all know about linear regression model. So what are the weights we are learning? We are learning slope and y-intercept, right? What is the line equation? Y is equal to mx plus c. Here we have y and x in the data set. And what are we going to figure out? We are going to learn what is the value of slope, that is m. What is the value of y-intercept, that is c. Okay, so these two weights we are going to learn when training. Those weights are nothing but model in linear regression. Accordingly, in neural network, so many weights we are going to learn. Okay, all those weights put together, we call it as a model. Once you fine-tuned the weights, once you figured out the correct weight, that's all. Your model is done. With the weights you got, you will be able to do wonders. Okay. In case of supervised learning, we'll be able to predict. In case of unsupervised learning, we'll be able to cluster. In Gen AI like GAN, we'll be able to generate new data. So the magic is behind the generator and the discriminator. So generator is represented as G, and the parameters are noise vector and theta G, which is nothing but weights. Okay. So what I mean by random noise, we'll see in the upcoming. Now here I put example uniform or Gaussian. Okay, uniform or Gaussian. 1 minute. Denny. ரொம்ப சத்தம் கேக்குது Denny. Professors, I'm really sorry. Okay. So generator model is represented as G, and we have Z as noise vector, which is nothing but if it is uniform, we are taking the range from -1 to 1. If it is Gaussian, we are going to take from 0 to 1. So any number, any random number will be generated based on the distribution. When we take uniform distribution, we get some range of numbers, or we also can use Gaussian distribution. There we are able to get some numbers. Okay, some range numbers. So anyway, what is a noise vector? We are getting some random number. That itself is an input. Okay, noise vector. What is vector? It is not only one data. We will have so many dimensions. Even you may have one data. So you may have so many numbers, collection of numbers in the range. This is known as noise vector. Okay, this is given as an input to the generator, and output we are going to generate the fake data sample, which is represented as G of Z. So the noise vector is P of Z, and the generated sample is G of Z. Okay, so G is a generator function. It takes a random input and it produces a synthetic data. That is a fake data. Okay, it is not a real one. It produces a fake data. Z is nothing but a random noise vector. It can be from any distribution, simple distribution like Gaussian distribution or uniform distribution. Theta G is nothing but the parameters of the generator, what we are going to learn. These are the exact weights and biases of the neural network that makes the model, right? Okay, so theta G is what the GAN trains. So during training, the generator is trying to adjust the weight. Okay, it will try to adjust the weight. Based on the weight, it will produce the fake data, right? To produce output, okay, and the discriminator should think that these outputs are the real one. Till that, the training goes on, right? Any doubts as of now? Okay, any doubt? If you have any doubt till, okay, please let me know. Please let me know. This is very important. You will try to learn the ultimate part. I'm going to make it very simple, right? Okay. So example for finding weights during training. How exactly we are finding during training? This is a base one. The same training can be applicable for generator as well as discriminator. Okay. Say, for example, I've taken a very simple data set, right? So what is the data set? We have 2, 4. This is all in the form of X and Y. X is 2, 3, and 4 are X data. 4, 9, 16 are Y data. So we have 2, 4, 3, 9, 4, 16, something like that. 5, 25, something like that. Okay. So can any one of you guess what is the underlying pattern of this data set? Can anyone let me know what is the underlying pattern of this data set? Am I making sense? Anyone, please? You can tell. Can anyone let me know what is the underlying function? What is the relationship between 2 and 4, 3, 9, 4 and 16? Can anyone tell?
Squaring, ma'am.
Very good, very good. So exactly, the function, the underlying function is square. If you give 2, the output is 4. If the input is 3, the output is 9. If the input is 4, output is 16. So exact square function is the underlying pattern. Okay, so that should be figured out. That should be figured out. We are giving us a data set. Ultimately, we need to get the pattern, the underlying pattern. Okay, so that itself is called training. Okay. Okay, yes, right? So y is equal to square of x. This is the underlying function in our example data set. And we need to represent this particular function using neural network. Okay, so in terms of weights, okay, how could I relate the function with weights, or how can I represent the function in terms of weights? Okay, yeah. Now representing the underlying function using a neural network with weights, right? Okay, so again, I'm taking the same example. Okay, so here the function is y is equal to x squared with the data points 2, 4, 3, 9, and 4, 16, right? So how do you represent as a neural network? You can go with the simplest single layer network, right? So you can use we could try with a linear. Okay, we can try with a linear, and we'll try to figure out whether the particular square function will be able to train or not. Okay, see, this is the equation of straight line model. Okay, this is the graph is the equation of a straight line model, right? So here in this case, it is a linear function. What do you mean by linear function? Whenever you will be able to predict y value with respect to x, we call it as using a line, we call it as linear function, right? You don't have any non-linearity here. But in this case, okay, this graph represents non-linearity. You have a curve, where in the linear graph, you don't have any curve, you'll be having only straight line. We call this as linear function. This line itself is linear function. So how does the line represent? How can you represent this line? In terms of slope and y-intercept, right? If you figured out the proper slope and y-intercept, that's all, the model is adopted. That's all, okay, here. But this particular function is square function, where the square function will not be predicted by using linear layer, because it is the square function is non-linear in nature. If you put and check, okay, if you put no, you'll come across a parabola, not a straight line. Okay, if you mathematically represent the square function, see, how do you represent? When the value is 1, the x value is 1, y value is also it is also 1. When the x value is -1, the y value is also 1. When the x value is 2 or -2, the y value is 4. Okay, when you go intersect and check. Okay, when the x value is 3, the y value could be 9, something like that. Okay, so you will be having the equation, here square function, you can represent in terms of parabola, not a straight line. So this linear function, or the linearity will not work in the case of non-linearity. Okay, do you understand? So single neuron, so this is single neuron, right? Y predicted is equal to, wait, this is nothing but mx plus c, mx plus c. C is nothing but y-intercept. This b is nothing but y-intercept here. This w is nothing but slope here in this case. Okay. With this one weight and bias, we will not be able to predict the non-linear function. Linear function only can be predicted by this single neuron. Okay. So we need to have hidden layer. So this function, y equal to x squared function is non-linear one. So by using single layer, we will not be able to predict. So this way is not approachable. We cannot, the single neuron, linear neuron cannot represent perfectly. So either we need to go with non-linear activation or with hidden layer. Now we are trying with a hidden layer with non-linearity. Okay. This is a simple feed-forward network. Okay. So we are having one hidden layer and we are going to check. So what is a hidden layer? Hidden layer, so this is a hidden layer, right? This is a hidden layer. So you have input layer, you have output layer, you have hidden layer, and you have various neurons in the hidden layer, right? That's what we are going to see, how many neurons could be worked for this case, right? So every neuron will be associated with its own weight. Every neuron will be associated with its own weight. And now we are going to see. Yeah. So this hidden neuron is equal to its own, the x parameter, the x value and the associated weight, W1. Every neuron will have its own weight. So x would have got its weight as W1, and this particular will also get bias B1. So you have to, as you know how perceptron works, W1 x1 plus W2 x2 plus bias. Here we have only one x parameter, so only one weight is there. So your hidden layer is nothing but W1 multiplied by x plus bias. Over there you are applying activation function called f. Okay, so using that h, you're going to predict. Okay, you're going to predict in the output part where that particular neuron will have W2 weight, and the hidden layer you're going to multiply and its own bias you're going to add up. Okay, so here also you will be able to apply the function, activation function, right? The activation function can be anything. It can be a sigmoid function, it can be a ReLU function, or it can be a tanh function. So we are going to check. Okay, so what do we optimize now? We are going to optimize W1, W2, B1, B2. Okay, these are the weights and biases in terms of theta G in Gantt terms. Okay, now we are going to see whether this is okay for y equal to x squared function. So we'll try with some numbers. So how does actually training gets? Training is done. Random numbers would be initiated. At initial level, some random numbers will be given to the weights. So it could be any number. Now we are trying with W1 is equal to 1, bias 1 is equal to 0, W2 equal to 4, bias 2 is equal to 0. It could be any number. It could be any number randomly. In this case, these are the numbers we have taken. Now, for x is equal to, what is our data set? X is equal to 2, y is equal to 4. X is equal to 3, y is equal to 9. X is equal to 4, y is equal to 16, which is nothing but square function data set. So for this x is equal to 2, we are going to check whether by using the weights, we will be able to get the y value or not. When you calculate in this way, we are going to calculate the hidden layer. So hidden layer is nothing but W1 multiplied by x plus bias. So 1 multiplied by 2 plus 0, bias 1, which is 2. Right? So your hidden layer, you are applying ReLU function. So it will give 2. Right? And but y squared, y had the predicted value. The predicted value, you are going to have this 4 again multiplied by 2. Okay, why? We are going to have this. Okay, W2 H plus B2. So we are going to, W2 is 4. Okay, multiplied by 2, that is H plus bias 2 plus 0. There we are getting 8. So what is the predicted value here? Hidden value is 2. For this x is equal to 2, hidden value is calculated as 2, and the y predicted value is calculated as 8. But what should be the actual y value? What should be the actual y value?
4.
Yes, actual y value must be 4. In the square function, accordingly, right? But it is overshooting. So what do we need to do? We have to adjust the weight accordingly, right? We need to have a smaller W2. Let me check again. W2 is equal to 2. Okay. And we are adjusting the weight from W2 equal to 4 into W2 equal to 2. We are adjusting. And again, we are applying the same and we are checking. Now the predicted Y will become 4 exactly matches. So with these weights, what could be the weight? W1 equal to 1, B1 equal to 0. Instead of W2 equal to 4, we have changed this W2 equal to 2 and bias equal to 2 equal to 0. With those adjusted weights, we are getting exactly 4. Right? Okay. We'll try with the next number, x is equal to 3. When we check out, we are not getting the actual 9. So what do you know? What is the essence here? One hidden neuron is very simple to approximate this function. So we go with 2 hidden layers and we calculate as such. Okay. So hidden 1 layer is calculated in such way. So you will have no for 2 hidden layer H1 and H2. You will have two neurons. You will have accordingly those weights W11, W12. Accordingly, you will have bias. Okay, so when you calculate, we'll see how do we get. Okay, these are the parameters now we are initiated and we are computing for x is equal to 2. Accordingly, this matches exactly. The predicted y matches with a real data set. When x is equal to 3, again, we'll check it is not till 9. We need some more training. So we have to train. This is all about training. Okay, so you have to fix up how many neurons must be there in the hidden layer and how many hidden layers must be kept in order to approximate the underlying function. Once the underlying function is captured by these weights, that's all, the model is done. I hope I'm helping you. Okay, right. What is the takeaway? What are the tunable parameters here? In this case, what are the tunable? What can be tuned? We can't tune x and y because it is fixed in data set. In data set, you cannot alter x or y. This is recorded value. That's all. You cannot change it. You are trying to figure out the relationship between x parameter and the y parameter. That's all. Okay, by means of weights and bias. So what are the tunable parameters here?
The weights and the bias, ma'am.
Very good. The weights and the bias are tunable. You can fine tune. You can tune accordingly till you get the correct prediction. You cannot, sometimes you cannot have 100% prediction, but still 95% prediction you are getting, it's okay. So that the unseen data is given as an X value. You will be able to figure out with the help of weights you capture and you will be able to find out the Y value. Got it clear? So this is what is happening during training. Okay, that's why we categorize the entire data set is taken and we are splitting as training data and test data. In training set, while training, the training data is taken for training, X and Y. We are going to figure out the relationship between X and Y. We are going to fine tune the weights and you're going to calculate the weights and fine tune the weights or captured weights. Okay, calculated weights or applied for test data. Test data we are taken and we apply over the X parameter. Whatever values we got, whatever function we got, we apply over the input parameter of test data. And we'll try to figure out whether we are getting correct data, that is predicted output, and the actual Y in the data set matches or not. Understood? So we say, for example, 10 rows of data we have, 8 rows we are taking as a training data, 2 rows we are taking as a test data, 8 rows training, X and Y, full data is taken, we are training, we are capturing theta, that is weights we are capturing, and the weights are applied over test data. Test data's input value. We are not considering Y value there. We are considering only X value and we are applying the weights over there. That is a function, revealed pattern over the X parameter. And we are going to predict what will be the output. Okay. Applying function or applying weights over the X value, we are going to predict Y value. That Y value, we call it as predicted Y. But in the actual data, in the tested data set, we have Y value. No, we call that Y value as actual Y. What is the challenge here? My Y value, the actual Y, should match with the predicted Y. If it is matched, that's all, the model is done. If it is not getting matched, we still train with the parameters. Okay, what are we tuning? We are tuning the weights. Okay, whatever weights, it's according to the architecture. How many hidden neurons you keep, how many input parameters are there, how many output parameters are there. Based on you have associated weights, all weights must be tuned. Right? This is what happening in training the data set. It is applicable even in GAN. Okay, so the for the nonlinear function like x square, multiple neurons are needed, or polynomial features are needed. Directly you can provide x squared value. So during training, what are we going to learn? We are learning the weights to approximate this function. What I mean by approximation? Once you figured out the weights, that's all. Any x value, if you give, it will be able to predict the correct y value. That is called as approximation. If you give 10, it should give 100. If you give 6, it should give 36. If you give 5, it should give 25. Something like that. Whatever number, it should be able to approximate. The entire function should be approximated. Right? Okay. So this is your architecture. Input layer is only one neuron in this particular case, and hidden layer, only one layer with 2-3 neurons you must have, and output layer is one neuron. This is your architecture for this particular example, and this is the particular architecture for our own example. So here you can keep only one X, and you will have only one Y. Okay, and you will have only one hidden layer where you will have 3 neurons. We have tested with one neuron in the hidden layer. That doesn't work. We have tested with two neurons. Even that is very simple. And we introduced 3 neurons in a hidden layer. It may work. Accordingly, you have to. That is the number of neurons. It will be while training it will be captured. Okay. So any function you can use. Like any activation function is okay. Probably, like multi-class classification, the output layer, you will have softmax layer, something like that. We'll talk about activation. If time permits, we may see. Right? So this is the underlying architecture of your just example case. How to decide a priori, ahead, how to decide how many neurons to be kept. Okay, how many neurons are needed. In input layer, number of input. In our case, only one input. In in fruit data set, we have 3 input. One is color of the fruit, one is taste of the fruit, one is weight of the fruit. 3 parameters. Okay, and Y is only 1 parameter. So how many input, okay, X1, X2, X3, something. How many number of features are there? Okay, in a data set, okay. What do you mean by feature? Colloquially, if I tell, your column name is a feature. Your column name, taste of a fruit, is a feature. Your column name, the domain, is called as feature. Feature is also can be told as parameter. It also can be told as dimension. Okay, so the number of features is equal to number of input neurons. Number of input features is equal to number of input neurons. So how many input features you have, that many input neurons to be kept. Okay, and how many? Yeah, in this case, see, if you have 3 features, you have 3 input neurons. It is not tunable, it is fixed by the data set. Understood? Okay. Next, output layer. Output layer also is not tunable because we have a priori in the data set how many output. Say, for example, you have 3 output, mango, banana, and orange. 3 outputs are there, 3 labels are there. So you have to classify either mango or banana or orange. So 3 labels must be there. Accordingly, you have to have 3 neurons in the output layer. Understood? We call it as multi-class classification. If there is only 2, we call it as binary classification, something like that. Okay. For regression, it could be a number. It is not a label. Categorical value means label. If it is a number, it is regression. Say, for example, how much rainfall you will have. Right? That's called regression. So number of output neurons depends on the problem, right, in the data set. Fixed by the prediction time. How do you predict? How do you predict? Okay. Hidden layers are tunable. Okay, these neurons are tunable. Okay, so if it is a linear function, you don't need to have hidden layers at all. right? And if it is continuous, accordingly you will be able to. That's a practical problem, and exactly what is happening, how exactly it is getting trained is a black box. That's why explainable AI comes into picture. Okay, it will try to track, okay, what is happening, right? So deep nets. When do you call a network as deep network? 10 plus hidden layers are there. Number of hidden layers are 10 plus layers. In each hidden layer, you will have so many neurons. You call it as deep network. Okay. For complex tasks, we need to have. Okay. The number of neurons in hidden layer, each hidden layer is a rule of thumb. Okay. So example, input 1, output 1, hidden layer may have 3 to or 2 to 5 neurons. Okay. So I know all of you would know what is overfitting or underfitting, right? Can I ask you what is overfitting?
Ma'am, if we are using a large, so much amount of data for the training purpose, maybe it can lead to overfitting.
Yeah, it try to memorize the model.
Yes,
For example,
yes.
it's like memorizing the book itself. If you
Yes.
a student other than book, no, he'll not be able to answer. He'll mug up the data. That model will mug up the data so that whatever you're asking from the data set, it will try to figure out the correct output. But
Yes,
outside,
ma'am.
it will not be able to figure out. So that's called
Yes.
overfitting,
So
right?
if it is underfitting, if you don't have sufficient amount of data for training, it leads to underfitting. And maybe the prediction might not be correct, the training might not be correct.
Yeah, even training error is huge, and testing error also will be huge. Training
Huge.
time also,
Yes.
it will not be able to figure out correct. It will not be able to capture the underlying pattern properly at all. We call it as underfitting. Exactly. Okay, right. So for this particular square function, input equal to 1, output equal to 2, hidden is 2 to 3 neurons, and yeah, this is the architecture. Okay, this is the possible network for our particular square function, right? Okay, so this is the thing. Okay, this is the overall summary of it, right? Okay, so now how does GAN model gets trained? How does it train? What do you give? In our training data set, we are giving 2 as an input, 3 as an input, 4. But here, what is the input actually? We are giving a range. Okay, we are specifying either it has to follow Gaussian distribution or either it has to follow uniform distribution. So any distribution, accordingly, it will take some random numbers. From -1 to 1, it will take any number, or 0 to 1. If it is Gaussian, 0 to 1, any number will be, random number will be picked up by the generator. That is called as random noise. Okay, usually from these distribution. Okay, this is an input for the generator. Using that input, using that noise, it will try to convert into real data. This is how we are going to see how. And its main objective is to fool the discriminator. And discriminator's goal is to correctly predict the generated data. Real is as real and fake as fake. Okay. So now we are going to see what is a noise vector. So PZ is a noise vector. If it is uniform distribution, we are going to take from this range. The numbers are collected or numbers are generated from this range, -1 to +1. If it is normal distribution, the range could be 0 and 1. Okay, and number of dimensions also matter. Okay, that many numbers will be generated. See, it includes 100 dimension, right? So how could be the input? 100 random numbers from this range, okay, is depicted as noise vector. Okay, this is latent space. So what is a latent space? These numbers will generate some image or some data. This tells the abstract or lower dimensional space, and it represents some data. Okay, we call this as latent space. Okay, the noise vector is a latent space. So this latent space is an abstract lower dimension space where each vector, okay, it comprises of many vectors. Each point is a vector, many vectors. 100 dimension means 100 vector. Okay, full 100 points would be there. That is known as vector. Okay, that represents some compressed feature or hidden features of data, right? So this is a space where random noise vector Z bits. Hope you all understood. Okay. So instead of directly generating an image, it takes a latent space and maps with the data space. Okay. We'll see how. So initially with these numbers, okay, with these numbers, it will try to generate some data. Okay. All right. So what is the intuition here? If you want to generate phases, for example, okay, the latent space can be anything, right? So with 100 dimension, this could be the latent space. This could be the noise vector. Each dimension doesn't have a direct human face, okay? But after training goes, okay, one fine time when model is trained, you will have realistic data as it is given in the data set. Initially, we are giving only the noise vector to the generator as an input. He doesn't know anything about the real data set. Who knows about the data set? Discriminator knows about the data set. This generator doesn't know anything about the data set. Noise vector alone is given. That too, the distribution is given. From the range, it takes some random number, it generates some, it is generating some data. Okay. So this is what is happening. Say, for example, after training, changing one dimension, okay, any particular dimension, if you're tuning, it will correspond to smiling with non-smiling. Already with smiling image you would have got. When you fine tune one particular vector, one particular value, you will be getting non-smiling face, glasses with non-glasses, lighting with phase orientation, something like that. Okay, so you're moving smoothly from latent space into a realistic image. Understood? Okay, so this is mathematically your generator function. G is represented as Z and theta G, which generates fake data. Okay, fake data. So G is a generator function. Z is a random noise, as I told you. Theta G is all about weights and biases. How it's pure deep learning model. Okay, you will have your input layer, you will have your output layer. In between, you will have so many hidden layers with maybe neurons. Okay, so the output is generated data is fake data. Say, for example, 64 cross 64 cross 3. 3 represents RGB, right? Okay, so your architecture could be something like a deep neural network. Okay, deep neural network, right? So you will have input Z comprised of 100 dimension, dense layer. In the case of image, you can instead of connected layer, you will be able to have your convolutional layer. How CNN works? Okay, why we are going from neural network into CNN? Because if you take image and all, so many 256 cross 2 or 64 cross 64. If you take you have that many input. Okay, so for those input, you have to have it in as a layer in your fully connected layer. I mean your neural network part. That many layers must be. That many input should be there. You have to have so many weights with the input. The computational part is very heavy. So in order to avoid that, what is done, instead of having those many X parameter, you are introducing CNN over there in terms of cooling and all. Okay, max, so many are there, right? So we are introducing, in order to extract the features, we are introducing CNN over there. After extracting features, the extracted features are given as an input to the fully connected layer, where followed by your classification using softmax or any activation function with the output layer. Okay, so in deep neural network, if the data is image data, you can very well go with CNN. Okay, we'll see later. So this is something like that. Okay, this is something like architecture. So what is your deep neural network consists of, right? Okay, so what is the goal of the model, generator model, discriminator model? Discriminator model is a neural network. Okay, again you have input, hidden layers, output layer. Okay, it is a classifier. It is a classifier trying to distinguish between real data and fake data. Whereas your generator model is trying to generate so many fake data that looks real, as if it is a real data, right? So this is a function. This is mathematically, we call this is a function. We call this as a value function, which comprises of discriminator model and generator model. And this first one, okay, is there for discriminator to evaluate real data as real data, and this is for predicting fake data as fake data. So your discriminator is trying to maximize the value, your generator should try to minimize the value, because it should not know, it is trying to fool. It doesn't know like the discriminator to inspect or know to find out the real, the generated sample's quality. So it is trying to minimize the value, and D function discriminator is trying to maximize the value, right? And this is Z data, like Z data, and this is this is X data, this is Z data. Z data is something called generated data. This X data is a real data set. Okay, so it is associated with this, right? Generated data set. Whatever is generated should be identified as fake data, and this should be identified as real data. Okay, vice versa, right? Hope it is clear. Okay, so the first term, when you figured out the first term, okay, X corresponding to P data log D of X. So this P data of X, real sample, should be, it is a sample of a real data point from the true data set. Your discriminator function is to find out the probability. Exactly, it will not be 0 and 1. The discriminator, the classifier is not exactly 0 and 1. That will be very harsh. It will give you the probability value. So the closer to 1 value depicts real. The closer to 0 value depicts it is fake value. So log of D, we want to this to be high for real samples. Okay. So in this case, the log value should be high for real samples. Okay. In the second term, okay, this is Z value generated. See here, DG of Z. So this is generated sample that is classified by discriminator part model, and it should be less. Okay, that should be figured out as fake data, right? So DG of Z is discriminator's estimate that the fake is real or not. So 1 minus this value, probability it's fake. Okay, so this particular term encourages the discriminator to assign lower probability to fake data. That's why we have given 1 minus this particular value. Okay, so the expected value Z of PZ, PZ is nothing but the generated sample. Okay, so your discriminator model is trying to learn, or it will try to figure out real data from, or it will try to make a difference between real data from fake data, right? So input is real. For this discriminator, what is the input? The input is the generated data as well as the real data. Okay, so real or generated data. Okay, real or generated data will be given to the discriminator. The data should be taken by the discriminator, and it should be able to figure out whether it is real or fake. Okay, the output is a probability between 0, 1, not exactly 0, 1. The probable value will be given. It is like a two-player Minimax game. So what is the role of the discriminator? It is a binary classifier. Though it is a binary classifier, we are going to see binary cross entropy that will give you probable value. So target value should be 1 or 0. Real sample, it should be 1. Fake sample, it should be 0. Okay. So we need for the discriminator to get trained, we need both kinds of samples. We need real samples as well as we need fake samples. Why do we need real samples as well as fake samples? Can anyone answer? In generator case, we only need noise vector in order to create the synthesized data. For this discriminator, we need real samples as well as fake samples in order to get trained. Discriminator model should get trained first of all, right? Real sample with the help of real samples as real samples, with the support of fake samples labeled as fake samples. How? Why? Can anyone answer? Please, time is up, please. Anyone? Can anyone tell me? Otherwise, if you don't know, please let me know. Are you all attentive? Are you all there?
Ma'am,
Tell me, ma'am. Why discriminator needs both the samples?
how will it know whether it's the real data or not? I'm sorry, my mic is.
That's okay, ma'am. Ma'am, are you able to capture the lecture, ma'am?
Yes, ma'am.
Is it fine? Okay. Yes, ma'am. I seriously want to help you, ma'am. Like, okay, so the answer is why noise? Why do we need noise vectors? Why do we the batch, the mini batch, the training, batch, the number of data, okay, we call it as a batch, mini batch, okay. So we are giving that as an input to the discriminator here, where we have m real samples and m noise vectors. So why do we need to have noise vectors for the discriminator? Why? Because while training, only then it will come to know what are fake samples and what are the real samples. Okay, so the real set tells discriminator what genuine data looks like, and the fake data set tells what the generator is producing right now. Okay, so while training, it needs both the data. All right. Okay. Yeah. Without fake samples, discriminator would only see the real data. Okay, and will trivially predict all our real samples. And without the real sample, it will predict all are fake by the time. So we need both the data to learn the difference. Okay, right. So this is how it will be trained. Okay, real data by using X. Okay, the weights are captured with a fake. Okay, with a Z. That is, this is X bar, which is otherwise known as Z. Okay, so weights are tuned up. So this is how it will learn. Okay, this is your loss function. So what is loss? Can anyone tell what is exactly loss? What do you mean by loss? It's 7:20 now, please. What is loss? Can anyone tell me what is loss? Okay, I'm telling you the difference between actual value and the predicted value, we call it as loss. Okay, after training, what is our expectation? We need to correctly predict the value, but whatever we predicted could be wrong. So the predicted value could differ from the real actual data set value. So the difference between predicted value and actual value, we call it as loss. If the loss is very minimum, then we can neglect, or accordingly, this is based on the application we take. Okay, so that's how we calculate the loss. The loss is the difference
Ma'am,
between actual.
It's like error. That means the actual value.
Yes.
That is already
Yes,
mentioned in the chat box. Did you miss? Okay.
Okay. I am not seeing in the chat box. Sorry, sir.
Okay, ma'am. Okay, thank you.
Okay, so the loss is the difference between your actual value and the predicted value. So that should be always less. Okay, that's why we are using gradient descent in order to fine tune the weights. Okay, that's how we go with back propagation and all. Okay, so here it uses binary cross entropy loss function, and this is the function. Okay, you all know what is a binary cross entropy function. This is for calculating the real data part, and this is for fake data. Okay, the loss could be calculated by using this log function. Okay, so applying this to the GAN discriminator, right? So discriminator part, real data should be labeled as 1 and the fake data should be labeled as 1. The loss distribution is the minus part for real and 1 minus D for loss contribution for fake data. So putting all together, this is your loss function. This is your loss function, right? Okay. So this is the architecture diagram. So you'll have generator generating fake images, and that will be given to the discriminator along with the real images in the data set. That will figure out, that will give that will classify, and that will give you, it will be trained by itself, and finally it will classify whether the data is real as real and fake as fake. And that output, okay, that output is given as a valuable input to the generator. Generator receiving the feedback from the discriminator, thereby indirectly discriminator is helping, police is helping the thief how to improve the currency, okay, fake currency, right? So it is getting the input from the discriminator. Generator is getting the feedback from the discriminator, and it is able to much, like fine tune the weights and all in order to create the fake images. And again, it is given to the discriminator along with real images. This time, while training, epoch by epoch, it will be trained. Okay, and because of the feedback given by the discriminator, a generator is capable of producing realistic images. At one fine time, discriminator is not able to discriminate properly, right? So this is the full architecture of GAN technology, right? So this is your general idea. Discriminator is just a binary classifier. Either it will be a real or fake. Okay, so we are training with binary cross entropy laws. That's why it is not harsh 0 and 1. It will give you a probability, as I told you already, right? So this is your binary cross entropy. This part. Okay, this is a function, right? So y could be 1 for real samples and y could be 0 for fake samples. This particular first part we call it as for real sample. The second one for fake sample, right? Okay. So we have seen this already. Time is this also we have seen. So what is exact loss we have seen? So in linear regression, what is the loss? All the data points over the line are actual y value. All these blue dots are predicted data. So the difference between the actual data point over the line and the blue data, blue dot, we call it as error. The difference between the actual data point over the line, for example, for this particular 20, the y value could be across the line. It could be something like a 7. Okay, so this particular point. So the data point over the line, we call it as actual data, y data, and the blue point, we call it as predicted data. The difference between the actual y value over the line and the blue dot, we call it as difference. We call it as error. We call it as loss. Okay, so that is being picked. Okay, that's being picked. And during training, the weights and all are being adjusted, and we are going to get the correct weight, approximately correct weights. So we have various loss functions. We have mean squared error, we have mean absolute error, binary cross. So many are there. Now we are using binary cross entropy for binary classification, right? So when to use what loss function is also makes sense. This is CMAI. Mean absolute error. This is mean square error. When to use this? Whenever we want to minimize the outlier impact, we are using this particular loss function. Whenever we want to amplify it, we are using mean square error function. So in this case, in GAN case, we are using binary cross entropy log loss. Okay, why? We want to correctly predict S as S, Y as Y, negative as false, real sample as real. Okay. Yes. So these are this thing, and this is the main idea for binary cross entropy. Okay, ultimately what do we do? Ultimately discriminator will give probability value for generated samples. Okay, if it is closer to 1, generator wins the race. If it is closer to 0, then generator is lost. Okay, is losing the game. So accordingly, generator will keep getting training and fine tune the weights. Okay, until it could produce the data which is similar to real data. So this is all about GAN. Okay, and these are the various types of GAN we have. It is broadly classified as architecture based and loss function based. Okay, so conditional GAN, we are conditioned. Okay, it is conditioned, right? It provides the generator and discriminator with some extra information. Say, for example, it should produce 7, something like that. The class labels are given. Okay, so GAN, C-GAN, conditional GAN is trained over the particular data set. It is conditioned to generate a specific digit rather than a random noise, random data. Okay, it is conditioned to produce some particular data. Right? A deep convolutional GAN, if it is the image data, you can use DC, CNN you can use. Okay, deep convolutional network, right? This is called as the C-GAN, and again so many variants we have, image to image translation, right? And pics to pics, okay, paired image to image translation. This we have from image. If you give a particular image, that will be converted into again one more image. Okay, how do we map from data to data? Say for example, pencil, we are labeling as pencil. Pencil image, we are labeling as pencil. Something like that. We are paired up image to image translation. Okay, you can group data, you can group images, right? And the style GAN, okay, it gives you, instead of noise vector, it gives no intermediate latent space as an input. Okay, so it will give you good quality images and all, right? Okay, progressive GAN is also one variant. It progressively grows, okay, with the low resolution, and it adds gradually as a layer, and in order to create a high resolution output. And super resolution GAN is also available for upscaling the quality. Okay, other notable variants are text to image, big GAN, and all. So many GANs are available. Okay, and with this I'll wind up. Hope it is useful for all of you. Any questions you can ask now. Thank you all.
Thank you, ma'am. Dear participants, you may please post your questions or queries in the chat box, or either you can unmute your mic and ask ma'am directly. Please.
Any questions?
Participants, please. And I request all the participants to kindly fill the feedback form for the session that is given in the chat box. Please don't miss out on it for your attendance. Ma'am, we think there are no more questions to come.
Okay, ma'am. Okay.
Shall we continue?
Yes, ma'am. Yes, ma'am. So I hope I helped you. Am I making sense, ma'am?
Ma'am, there couldn't be a better session on GAN actually. And so it must have sparked some research insights into some people at least who have joined the meeting. Now, I would like to invite Ms. Shefi Agustin for official vote of thanks from our part, ma'am. Shefi, please.
Yeah. A very good evening to all. On behalf of everyone present here, I take this opportunity to express our sincere gratitude to Dr. Mercy Paul Selvan for delivering such an insightful and engaging session on generative adversarial networks, concepts, and applications. Your clear explanations and valuable insights have deepened our understanding for this cutting-edge topic, and I'm sure it will inspire many of us to explore further in this area of research. I also extend my thanks to all participants for your active involvement, which made today's session more interactive and meaningful. Once again, thank you, ma'am, for sparing your valuable time with us and enriching your knowledge. Thank you.
Thank you so
Thank
much,
you,
dear.
Shefi. Ma'am, once again, from our management faculty and the Nirmala College fraternity as such, we extend our hearty gratitude to you, ma'am. And as I mentioned before, we couldn't have a better session on GAN. The link between generator and discriminator was really beautiful. You made it sound so simple. Thank you so much for that session, ma'am. Thank you.
I'm excited to give you this lecture, ma'am. Actually, my situation was so horrible. My husband is in hospital. Yesterday, he had a heart attack, and when I came for the session, he was in ICU. So he's shifted to ward. Kindly pray for us. Thank you so much. Thank you so much, ma'am. Thank you so much.
Yes, ma'am. Surely we'll remember you and your family in our prayers. We did get to know about the medical situation yesterday, so we were praying that you will be able to join today. And we are really grateful for you for taking this time off to give us this session.
Thank you so much. Sir who we are communicating, he's so helpful. Yeah, Sharin's, I don't know his name actually, is very humble person. My heartfelt thanks to you, sir.
Thank you, ma'am.
Yes, sir. You could understand the situation. He did not know, like, panic me, or he did not know, did anything more. No, like, he just tried to understand, and I'm very grateful to you, Sharin, sir. Thank you so much, sir.
Okay, thank you.
Thank you.
Okay.
Thank you, ma'am.
Thank you.
Thank you, Sherry,
Thank
ma'am.
you.
Thank you, ma'am.
Thank you. Thank you so much.
Thank you, ma'am. Thank you.
And dear participants, I would like to remind you to kindly fill up the feedback form given in the chat box, as well as it's been shared in the WhatsApp group also. So please don't miss up on the feedback form. Now, we would like to move on to our next session of the day. We do have amongst us Dr. Ragesh, Associate Dean for Industry Relations and Funding at the Indian Institute of Information Technology, Kottayam. Sir is with us today to handle the topic on AI-driven intelligent connectivity for cyber-physical systems in next-gen networks. I would like to invite Ms. Liji Jose, Assistant Professor, to introduce our resource person. Liji, please.
Thank you, ma'am. Good evening to all. We are honored to welcome Dr. Rajesh GK, Associate Dean of Industry Relations and Funding at the Indian Institute of Information Technology, Kottayam, an institute of national importance under the Ministry of Education, Government of India. He is a senior member of IEEE and an active academic leader, innovator, and researcher. His expertise spans cyber-physical systems, Internet of Things, UAV drone technologies, wireless networks, AI-driven secure communication systems. He has led multiple nationally and internationally funded projects with agencies such as DST, DRDO, IGSTC, and ANRF, and has established cutting-edge labs at IIIT Kottayam, including the DroneX Lab, Create Lab, and GAN Innovation Lab. Dr. Ragesh has authored numerous publications in reputed journals and conferences, holds patents, and actively mentors PhD scholars and students. He is also known for building collaborative ecosystems with industry and academia across India, Europe, and Southeast Asia. Today, we are privileged to have Dr. Rajesh with us to share his insights and expertise. Let us extend a warm welcome to him. Over to you, sir.
Thank you. Thank you for your nice introduction. And thanks, Sherry ma'am, as well as Liji ma'am, for inviting me to be a part of this Atal FDP program. Hope my voice is audible.
It's audible, sir.
Okay. Since I'm not using any mic, I'm directly speaking out to my laptop.
Yes, it's audible.
Okay. So today I'm going to give you, I don't know like what is the kind of talk title which has been mentioned, but for the time being, this is again a kind of cyber-physical system stuff I'm going to present, but I will try to, club it with this AI IoT because we cannot make any standalone technology nowadays. We need to have its assistance from AI techniques to make IoT systems, to make cyber-physical systems. So I will try to share my slide once again. Sorry, one second. I'll share my complete screen. Slides are visible now,
Yes, sir, it's visible.
right? Okay. So
Yes.
the title of the talk is AI-driven intelligent connectivity for cyber-physical systems in next-generation communication networks. So this talk will be useful for someone who is interested in wireless communication, like who is interested in developing certain products related to AI with IoT for different kinds of use cases. So here I will give you so those who wish to do some kind of research in AI based IoT, it will be useful because I am going to give you some kind of research directions as well in 5G 6G area. And 6G, that this is full of AI driven. So, the complete picture will be like, first I will be giving you some idea about IoT, then we move on to connective technologies, then different use cases, then what is 5G, then what is the vision for 6G, and some research directions, security, privacy aspects, etc. So I understand that there are 73 slides available in this PPT presentation. So I hope I will complete it by 9 p.m. Okay, I don't know, because continuous kind of sessions, I don't know how much you can, pay attention to such kind of sessions, but I hope I will try to make the sessions more interesting with some use cases. Okay. So this is a flow of presentation. I will try to introduce what is IoT, what is cyber-physical systems, and how these IoT and CPS are related to each other, and the communication capability, the communication facilitators for establishing such kind of IoT ecosystems. We need some strong communication support. So for that, we are using 5G communication networks, 5G cellular communication networks, as well as 6G communication networks for that. And I will try to introduce some kind of components in IoT and CPS. And through that, we could understand what is the synergy between this IoT and CPS. Then different standards, protocols, different use cases of IoT and CPS. Then, architectural things like IoT architectures, 5G architecture, etc. Then what are the enablers, technology enablers for 6G, and how these 5G, 6G is, assisting IoT, AI-driven IoT networks, and what are the research directions in this area. So this is the overall idea of this presentation. So you can, since I'm not seeing any one of you, I'm only saying this PPT. So if you want to stop me somewhere, please do that. Okay, do not wait for the sessions to be over. You can ask questions in between as well. Okay. So I will start with some introductory notes about the communicating world. Before going directly to IoT and CPS, we should understand that why we go for such kind of systems. Because you know that now this is not like, more than human, devices are communicating with each other. A lot of connected devices are there. And there is an increasing demand for, data rate. We know that we are not satisfied with gigabit per second speed also. And we do not sacrifice our batteries for that. So that's why extended battery life is another important need. And the third thing is, we cannot wait for anything nowadays. We need immediate results. We need to, the actions have to be happen in split fraction of second. So that's why the third important, parameter that we are looking at is the end-to-end delay or the latency, right? Reduced latency. So this is a vision of a communicating world. We have billions of devices, millions of devices communicating with each other. They're all kind of data generators are devices, not human, right? Before that, when we discuss about the third generation, fourth generation kind of networks, the data was generated by humans more than, devices. But now it's reversed. The data is more generated by devices more than humans. So there is an increasing demand for connectivity, an increasing demand for better data rates, better bandwidth without sacrificing the batteries. And we need, everything to be happen within split fraction of second, immediate actions to be happened based on certain commands. So reduce latency, right? So that these kind of, so no single technology can serve all these demands. No single technology, even AI or IoT independently cannot satisfy the demands of the user community. So that's why there is, there is an amalgamation of various technologies are there. A cross-domain approach we need to go for, integrating, the sensing elements. We start with something because this is towards a world of automation, right? We do not want any human to operate anything. We want machines to understand things, machine to respond and automate everything. So that's why there is an increasing demand of integrating different sensing elements. We do have, low cost embedded systems we need, low cost embedded systems, because, this is the number of devices which we are using in such kind of wireless communication world is massive. So we cannot go for higher devices. We need to have low means, tiny embedded systems with cyber physical systems in place. CPS, I will explain CPS in the coming slides. Then device to device communication, that. We usually call it as machine to machine communication, or if I am adopting the terminologies from 5G, 6G setup, I can say that this is a massive machine type communication, MMTC. Massive machine type communication. Okay. So usually we call it as device-device communication, but when we are describing a device-to-device or machine-to-machine communication in a 5G, 6G perspective, this is all about a massive machine type communication, MMTC. Okay. And here, 1 second, I will hide this. And 5G wireless systems with IoT as a center. So IoT will be a common technology enabler, but we have multiple amalgamation of technologies in between. You can take AI here, because in order to provide some intelligence to the work, we need AI, along with IoT sensors, cyber physical systems, where we have more monitoring and control. Okay. So IoT, you know that it's about connecting devices, machines, different objects, different things, I can say. That's why it's called things. Things could be anything. Thing could be human. Thing could be, any physical object. Okay, anything. So machines, it could be process, it could be tools, etc., which can communicate, exchange data between each other with the help of internet. Okay, that is IoT. So according to NASCOM and similar kind of, Gartner research and all, the, at present point of time, we have over 9 billion things connected to the internet. Okay, according to the NASCOM as well as the Qualcomm website, I have read some white papers from those websites. From that, I could understand that for every Indian, at least 7 different devices are being connected to internet. It could be in the form of your e-watches, your pacemakers, your mobile phones, your tablets, laptops, your home Wi-Fi, everything. So it's all your Alexa devices. So all these, at least 7 of devices of an Indian is always connected to internet, as per NASCOM research, as well as, the Qualcomm company research and all. So things connected to the internet are projected, in the coming years, it has been projected to cross around some 20 billion in the near future. And you can find a unification of different technologies, because many of these IoT devices, you can say that it is coming under wireless personal area network. Wireless personal area networks, that these are the networks which can exchange data around a person's operating space, around a person's personal space. So that's WPAN. So you can find such kind of technologies like your Zigbee, your Bluetooth, etc., which is part of this IoT ecosystem, which are found to be connectivity technologies of IoT, which are coming under this low power, low range communication technologies. And the devices which we are using in such kind of low power, short range wireless communication technologies are nothing but the low power embedded systems. Then cloud computing, in order to provide, so we need to process the data somewhere. You need to store the data which has been collected by these sensing devices, so that some knowledge can be generated out of it. So for that, you need some kind of infrastructure. You need cloud computing infrastructure, or edge computing, or a fog computing. And the data that is being generated from all these networks are, comes with different varieties. So usually we call it as 5 V's, right? Variety, veracity, and on. Velocity, all those things. So big data means the data produced by all these connected devices, which is very huge. The volume is huge. And, you need to apply your machine learning algorithms there, so that, you can convert these raw data, which has been collected by these sensors from an environment to some, intelligent outcomes. So for that, you need to apply some algorithms and machine learning algorithms there. And, since heterogeneous devices are being a part of IoT, you need a proper networking infrastructure that can provide sufficient bandwidth, which is elastic in nature, so that, scalability in nature, because more number of devices are being attached to such kind of networks, so that it should not compromise on the quality of service. You know that what is maybe quality of service, right? Quality of service in terms of bandwidth, quality of service in terms of energy efficiency, quality of service in terms of your data rate, etc., etc. So networking infrastructure should be proper. So IoT is not at all a stand-alone technology. This is a unification of different technologies consisting of different low-power embedded systems, devices, cloud, computing infrastructures, big data, then machine learning algorithms, and a proper networking infrastructure. Okay. So this is a definition given by Gartner Research. You can find n number of definitions. This could be a common generic definition when some of us can easily, someone asks you like what is IoT, you can easily answer this. So IoT is the network of physical objects that contain embedded technology to communicate, to sense, or to interact with the internal states or with the external environment, right? So IoT is all about, if you could, in generic terms, I can say that if you could put some, sensing elements to some objects which can sense, which can process it, and which we can forward it to some other similar machines or some other similar entities, objects with the help of internet. Okay, then we can say such kind of an ecosystem is an IoT ecosystem. So in that ecosystem, communication can happen internally also, and also with some external environment. Okay, like Bluetooth devices communicating with internet, like with the help of Wi-Fi or 5G or 6G kind of network. So it could be like internal communications happening, as well as extending that communication over a few more miles with the help of other technologies. So that is known as IoT. This is the famous definition by Gartner Research. And these are some of the components of IoT. Starting with, we have, I understand that many of you have learned about computer networks and all, right? So there itself, we know that we are following some kind of layered architecture. The kind of layered architecture is being, extended. Nowadays, that we have the OS architecture and all, and this OS architecture is just a kind of theoretical model. And the theoretical model is extended to a working model with the help of TCP over IP. And the same thing again extended to some other kind of new gen technologies like IoT. So here, the common definition, the common architectural layer setup of wireless remains the same. Here also we start with the physical layer, or we can call it things layer. Things layer here, we have different objects in place which can sense the environment, which can process it, and can be transferred to a local network. Okay, local network like your personal device assistant, a PDA, could be a local network. And from that local network, with the help of internet, it can be forwarded to the next end, a remote location, where these data collected from one single location, multiple locations, will be synthesized, will be processed with the help of your machine learning algorithms and all, deep learning algorithms and all, so that a knowledge can be created. So we are actually converting raw data to information and information to knowledge, right? So here we can see that we have things in place. We have a local network. In a local network, that you can take examples like Zigbee, Bluetooth, your LoRaWAN, and all those things comes from the local network, the normal things. Then we have the internet. You have the backend services, where the final results will be displayed in some dashboards. Some dashboards, from that the feedback will be, this is kind of a closed loop. A feedback will be again going to the the source generation side, the data generation side, so that the corrections can be done there. Okay, but in IoT perspective, it's only about sensing and communicating. If there is a feedback comes in, and depending on the feedback, some corrections are being made, then that IoT will slowly become a cyber physical system. Okay, CPS. So IoT is a subset of CPS, or I can say CPS is a superset. That the major ecosystem is CPS. In that, IoT is one of the technologies. Okay, so we have communication here, communication capabilities, communication infrastructures. We have processing, using your microcontrollers and all. Then we are doing some analytics out of it. We need to convert all these raw data into some actionable outcomes. Actionable outcomes. Otherwise, there is no need of IoT, right? So the whole idea behind IoT and CPS is, a world without any human intervention, completely managed by machines, theoretically speaking. Okay. So analytics is there. Then we have a permanent storage kind of setup where you can do filtering, processing, and the knowledge generation and feedback and all those things. So slowly I'm moving on to the second part, that is cyber physical systems, where you can find the integration of computation, networking, physical processes and all, right? So here, one more thing is available, one more thing is added when compared to IoT. Monitoring and control is there. That is, actions are being made with the help of, a feedback which is coming from the, from the knowledge, what kind of feedback to be given. So for that, physical processes, actionable outcomes, etc., is a part of CPS. Computation is there, networking is there, as well as physical processes. So unlike IoT, the prime focus is on connectivity and data exchange. Okay, but on the other side, CPS mainly emphasizes the integration of cyber elements, cyber components with physical components to create a system which is capable of interacting with real world, doing some actions to real world, depending upon the commands, depending upon the feedback that has been received from a remote environment, nothing but with the help of these sensing devices. Okay. So CPS, that the one fine example, is it can be found in your autonomous vehicles, self-driving cars and all, your smart grids, your advanced ubiquitous healthcare management systems, like your smart healthcare, where precise and timely interactions between digital and physical is at most needed. There is no compromise, right? So imagine the CPS as a robotic surgery machine using in hospitals, in operations and all. So, there is no compromise on delay. There is no compromise on reliability. There is no compromise on efficiency, right? So here CPS is all about that. Like, whenever you need an action to be happen in real world by getting the commands from the sensing devices, which is somewhere in a remote environment, okay, without any delay. So you are saying like, when 5G, 6G are in place, we are saying like, it should be 0.000001 second. Okay. So this is all about, the CPS. So for that, in order to make that intelligence to such devices, what we need an AI enabled. So that's why in some literature and all, you can see that this is not the normal IoT. This is AIoT. That is artificial intelligence assisted IoT systems. Okay, AI assisted IoT. Or sometimes people will say like AIoT, artificial intelligent, like Internet of Things, IoT. Okay. So these are the differences between all these things like components, IoT, and CPS. So we have, the elements are most common because CPS, the environment itself, is a part of IoT. So the components are the same. Sensors are there, actuators are there. We need connectivity, we need data processing, and we need a software for that. So sensors, that in IoT, like, we are using different kinds of sensors for understanding the different attributes of the physical environment. So those attributes commonly are temperature, pressure, vibration, humidity, anything, motion, etc. And this is all about IoT, collecting the data. But cyber physical systems, what it will do, like, it is essential for these data collected from sensors are essential for monitoring, inverted comma, monitoring the physical processes, collecting the real-time data. Okay. Then actuators. So actuators, know that we have sensors, we have actuators, right? So based on the command from sensors, actuators will perform certain actions, right? Like your robotic arm and all, providing some commands and robotic arm action, depending upon the application. So actuators, best examples are like, whenever you're asking your Alexa to turning on the lights, adjusting thermostats and all those things, then, execute physical actions in response to computational commands like robotic arms, valves, and all. So here, in cyber physical system, there is no compromise because of delay, time, and performance, the throughput, and all those things should be like pakka. There is no compromise on that. So so all the essential the data collection happens at the IoT ecosystem, and depending upon their data, the cyber physical system will do some actions, right? So because you can see the examples noted down here. Actuators, turning on lights, adjusting thermostats and all, where we are not much care about reliability part. We are not much care about efficiency as that of robotic arms, because robotic arms are actually using in Industry 4.0 production houses, right? Like logistic handling and all those things, where reliability is a must there. And also, as I said earlier, like in a robotic surgery environment where we cannot compromise on those things. So that's why there are two different angle perception is there, even though the kind of explanation actuators is somewhat similar as that of IoT and CPS, but more emphasis on reliability, more emphasis on latency, etc., is that for CPS. And connectivity here, we have local connectivity as well as a broader connectivity. So enable communication between devices and systems through the internet. You can use Wi-Fi, Bluetooth, Zigbee, LoRaWAN, Sigfox, 6LoWPAN, and many other kind of wireless technologies are there. Cellular networks, and here ensures seamless that those things are, even though this is a word, but it has a deeper meaning here. Ensures seamless integration and data exchange at any cost between cyber and physical components. That virtual reality environments and all, whenever we are building a digital twin means that when we are mimicking the real world things in software, those things, the actions, the interactions between different sensing elements to be seamless as that of the real world, right? So ensure seamless integration and data exchange between cyber and physical components. Data processing, we need cloud computing, edge computing, depending upon what kind of application that you're using. For autonomous cars, for self-driving cars, and all, we don't prefer cloud computing. Why? Because there is a huge delay from data collection side. The data is to be collected, processed, then forwarded. So everywhere a time element is mapped. For example, time T1 for data collection, time T2 for processing, time T3 for getting connected, time T4 for forwarding the data to the cloud, time T5 for processing, giving a kind of response from the cloud back to the source generation side. So this itself is a time, like lot of round trip time is huge here. But in the case of edge computing, why we go for edge computing? Because for autonomous cars and all, we cannot sacrifice the time for that. If you want to make an immediate action, like if some pedestrian is crossing the road, automatically the car is pressing the brake automatically. We need the split fraction kind of response is needed. So for that, we cannot rely on cloud computing infrastructures. We need everything to be there in the dashboard of the car. The decision has to be right from the dashboard rather than going to some Amazon cloud and getting the feedback. Those things, these are life critical mission applications. We cannot compromise on the latency part. So that's why the seamless integration is very important here, and that's why these things are closely connected. Seamless integration with cloud computing, edge computing, and all. So here, data processing as CPS, that this is real-time processing and decision-making capabilities. Real-time algorithms are needed. Then similarly, like software, we have more control algorithms and more system software for managing physical cyber components in cyber physical systems. Then networks, we know that a common infrastructure is needed, IoT infrastructure is needed, for both physical components, devices, and objects that are connected to the IoT. Then cyber physical components, data servers, cloud infrastructure, etc. Then the major thing is how you are communicating with the cloud. So here in IoT, we have many, standard protocols which are using in constrained environments. Constraint means what? Constrained on different, different computing resources, like in the form of bandwidth, in the form of energy efficiency. Batteries, in wireless communication, battery is a major constraint. So how can you do that? So there are two different protocols in IoT setup, which is prominent, they are following a different kind of communication architectures, but these two protocols, MQTT and COAP, these two protocols are found to be the popular one in IoT applications. Okay, so MQTT is a message queuing telemetry transport, and COAP is a constrained application protocol. Okay, so the communication models are different. MQTT is following a kind of publish subscribe model, that like your YouTube, someone is publishing their data and those who are interested in their data will be subscribed to it and use it. Similarly, MQTT is similar to that of your YouTube. But in between, in MQTT, we have subscribers and publishers, and the managing of publishers and subscribers are through brokers. So you may be knowing our AWS kind of thing, or your Mosquito, open MQTT platforms like the Mosquito or HiveMQ kind of thing. COAP on the other side, this is again a kind of a popular constrained application layer protocol, but it follows a model like a request response model, like your HTTP. Okay, request response model, like similar as sort of HTTP in traditional networks. Okay, so again, I'm not repeating it. Somewhat, the same thing will be repeated here. So I'm just moving on. So an example of IoT implementation has been shown here. As I told you, we have different sensor modes. We never call nodes here, even in computer networks and in many communication networks, we usually called as nodes, not modes. So here is a mode because it is having the capability of both sensing and processing. Okay, and we have a gateway. So the data which has been collected from that remote physical environment is being forwarded to the internet with the help of a gateway. So gateway allows the packets to go and come, like to let them forward and receive. Then we have a proxy server there. The proxy server is something like it can do some kind of security things like encryption. Proxy encryptions are there. It can do some level of filtering also before forwarding everything to cloud for analysis, right? And it has been interacting with internet, and we have protocols, WebSocket protocols there interacting with the cloud server. And the cloud server, that the data will be stored and it is being synthesized, processed and it will provide the right analysis, that can perform certain actions like switching on the bulb, as shown in the picture, actuation. So performing some actions based on the analytics given by the cloud, right? So this is the normal, the generic setup of IoT. Oh, I'm sorry. Yeah. So you can find enormous applications of IoT and CPS in many sectors. It can be from your manufacturing, we are discussing industry 4.0 nowadays, like production, everything, managed by machines itself without any human intervention. And what's the purpose of CPS? CPS will give you, it's all about, optimization. So here you can find the influence of AI. AI optimizations, AI can give you some predictive maintenance. If any anomalies are there, it can intimate immediately. It can give you some scheduled maintenance, etc. Process optimizations. So CPS, the major enabler CPS is AI itself. It's AI-enabled CPS, right? In the same way, smart grids about how different household or industry are using energy, right? Usage, generation, etc. So CPS again manages real-time energy distribution and grid stability. And you know that there is a concept known as, uh, prosumers. Prosumers means nothing but the one which can produce energy and it can consume. The other one will be consuming energy. Like here in our majority of Kerala houses nowadays are having, they are generating electricity, right? Uh, but I don't know whether KSEB is helping it or not. But again, in developed countries and all, when I went to Germany for as a part of a project and all, I can find that every single home in Germany, they're actually producing electricity, and they're actually providing electricity to their neighbors without any intermediate agency like KSEB. Okay, so those fellows, they normally called as prosumers, producer plus consumer. That's so smart grid. So CPS is an enabler for that. Then healthcare systems, you know that there is an area known as wireless body sensor networks, WBAN, wireless body area network, or WBSN, body sensor networks. So there, the human body wearing all these sensor nodes, collecting human vital data, forwarding this data to the next scope, to some cloud infrastructures where the medical personnel are sitting, and they will be giving some diagnostic treatments back. So that's a healthcare system. This is again, with the introduction of IoT, the WBAN terminology slightly moved on, slightly changed into IoMT, Internet of Medical Things. Okay, so IoT enabled medical devices, your fitness trackers, your pacemakers, etc., examples of healthcare systems, or even you can go to a website known as Shimmer Sensing, SHIMMER, Shimmer Sensing website, which is one of the famous provider for such kind of sensing elements. So those who are interested in developing any ubiquitous healthcare management systems, so WBAN, etc., in your lab, you can go to that Shimmer Sensing website. Okay, you can find n number of healthcare use cases, like how you can use EEG for a brain mapping interface. Okay, ECG, EEG, your Galvino sensors, multi-sensor fusion setups are available in Shimmer Sensing website. You can go and Google and find out some of the use cases under these healthcare systems. So CPS provides real-time monitoring for such kind of critical care. Sorry, I'm moving here and there. 1 second. Sorry. Okay. So some of the other challenges, some of the other applications are smart cities. You know that I will provide you some examples as well. Those people who are interested in seeing all these things, don't underestimate our Cochin city. Please don't underestimate our Cochin city. Someone saying, I still hear that, how can we say that Kochi is a smart city? Kochi is a smart city not because of metro. It is because of some of the intelligent innovations happening under smart city mission. Okay, you can go to Palarivattam, Kochi Palarivattam. There's an office for smart city mission where you can find all these things. Controlling traffic, I don't know how much it is efficient, but there is a huge dashboard available. There is a controlling elements available. Even live Kochi traffic is being monitored. Individually, we have very good AI cameras working over there. I personally visit such locations as a part of our project and all, tracking traffic, parking areas, whether improper parking is there or not, air quality index monitoring, and under this Kochi Smart City mission, they have deployed many solar panels in many places, like that like Kalamasheri area and all those areas. They have some solar panel implementations are there. They're lively monitoring how much solar energy is being consumed, how much is left, etc. All these things have been monitored. So smart city mission. So how this is possible? This is all because of all these sensing elements and cyber physical systems, IoT and GPS. Then autonomous vehicles. In the coming, I have many slides to present on that. Precision agriculture. Nowadays we are also doing smart agriculture with the help of Kerala Agricultural University, KAU, as well as Rubber Research Board of India, RRI. So where we are using drones for that, for drone irrigation, drone pesticide, management and all those things we are doing, and identifying weeds, etc. We are using it. So these are all part of IoT CPS. Drone itself is a flying IoT, right? Then building automation, like normal temperature, energy usage, and all those things. So these are the, in order to work all these things, we need some kind of standards and protocols that could assist IoT and CPS to work in such kind of real world applications. So MQTT, COAP, etc., those protocols actually take the first seat in standards and protocols of IoT. So MQTT, which is, I told you, like a lightweight publish, subscribe messaging protocol, ideal for IoT applications with low bandwidth as well as unreliable networks. And COAP, designed for resource-constrained devices and networks, used for IoT applications like smart grids and healthcare. The only difference is the communication model. The other one is a publish subscribe. This is all about the request response model. So HTTPS, standard protocols for web communication, widely used in IoT. So as data for traditional systems, we are using HTTPS in many IoT applications. Then, network protocols like IPv6 we are using, 6LoWPAN are using, because 6LoWPAN, majority of their devices are very cheap. Sensor devices are very cheap. They have very little memory. They have very little processing power. Because of that, the signal cannot, travel long distances. So that we are using, some context-aware kind of protocols like 6LoWPAN. And the data which is being forwarded usually follows formats like JSON as well as extended markup language. And we have protocol buffers in place. We have serial communication protocols, that I2C kind of thing. Okay. Then, some security standards are there because this is an open dynamic network, always wireless. When we compare wireless networks with the wired, the major issue is security, because anyone can join the network and leave the network without any kind of, prior notification. That's why, this is actually evolving from our mobile ad hoc networks. First, we have a wireless network. Then people think about why can't we make all the objects moving? Then it becomes a mobile ad hoc network. Ad hoc in the sense we cannot go for a heavy infrastructures. We need to set up infrastructures at least cost in some emergency conditions like disaster response kind of thing, natural calamity areas and all. Then people think about, can we give some sensing into those mobile nodes? Then it becomes wireless sensor networks. Then now people think about, can we exchange data with the help of internet? It becomes Internet of Things. So this is the evolution. So here, protocols are somewhat similar. When we migrate from one technology to a newer one, we are actually not developing from the scratch. We have something to be extended. We can use sometimes some compatibility protocol will be there. So that's why HTTP, HTTPS, etc. is a part of IoT. Then TLS, SSL, security, because security is a major concern here. We have security problems in every layer. Like, when physical layer, we have problems on jamming, eavesdropping, all those stuffs are there in, physical layer. When we move on to data link layer, like network layer, major network layer, we have man-in-the-middle kind of attacks, spoofing, and all those things are there. So for that, we need some kind of security standards. We have TLS and SSL. So transport layer security protocol, SSL protocol, and many of you may be knowing this. Then OAuth, it's a token-based authentication protocol. And we have a little bit lighter protocol known as a DTLS, data link layer based protocol, but it's a kind of a close-layered approach. So provide secure communication on the top of user datagram protocol, UDP. And you know about the standards. So who defined IEEE, IETE, and ETSI? These are all the big giants who developed such kind of global standards and protocols. So these are the different enablers for IoT. So we can see that IoT is not at all a single standalone silo kind of technology. We have a connectivity in place. We have different implementation across different sectors like mobility, agriculture, vehicle-to-vehicle communication, smart buildings, smart cities, smart grids, smart water, okay, underwater communication networks, etc. We have fintech. Even IoT is been a part of banking itself nowadays. Smart factories, medical sector, your social media networks, IOP, Internet of People. Then we have all the kind of connectivity technologies working in the local network as well as above the local network, like Zigbee, RFID, that Bluetooth, Wi-Fi, LoRa, LoWPAN, 6LoWPAN, and Sigfox, your cellular communication networks, etc. And other key enabling technologies are nothing but, especially without AI, we cannot imagine any kind of real-world IoT application. So AI occupies an integral part of IoT. Then we have big data, deep learning, and similar other kind of stuff. And similarly, we have the connectivity layers starting from local connectivity, as I mentioned earlier, RFID and all those things are in the local connectivity. Then we have gateway, which can connect to the internet, and different services are being provided. And you should understand that the different services means different demands. The demand which is foreseen by a healthcare unit may not be as that of an agricultural unit, because their reliability will be the first thing, security will be the first thing in healthcare. But in the case of in agricultural sector, it may not be the prominent the priority demand on the performance parameters. So the performance parameters, the quality of service parameters, that urgency, the priority will be different for different applications. Okay, so that's why there comes the importance of 5G and 6G. I'll tell you later in the coming slides. Okay, so the connectivity, local connectivity service providers, IoT management and all, and terminological interdependence. So here you should understand that IoT is everywhere. So you can see that it is a part of Internet of People, it's a part of Industry 4.0, it's a part of environment, or I can say Internet of Everything. There's a slight difference between IoT and IoE. In IoT, it's all about physical objects. We are not considering human as an object there. But in the case of Internet of Everything, we are actually extending the capabilities of IoT. The scale of IoT little bit extended, where the data generators are assumed to be humans as well. So that's why we have Internet of Everything as well. So it is extended capabilities. Then we are achieving autonomy in IoT with the help of CPS alone. So that's why CPS, the major responsibility is to give autonomy to IoT systems. Okay, so that's why IoT is not a single system, it's an ecosystem combining all these things and different machine-to-machine things, starting from your home, smart home to smart city, etc. Right? Smart, so several examples, several user logos, that object logos, object images has been showcased here. So publish subscribe model, as I told you, this is the model which has been followed by MQTT, like a publisher on one side and subscriber on the other side, and they cannot directly communicate. They can communicate only with the help of broker. So broker, for example, I told you about some of the popular brokers that we're using in academia, usually like HiveMQ or MQTT protocol, sorry, HiveMQ and Mosquito. And in order to simulate all these things, either you can use your Python language, or for my lab, since I'm teaching MTech and some courses for PhD, I'm using Node.js for them. Node.js is an intelligent platform where someone can create different IoT applications. So we can demonstrate easily MQTT, that publish subscribe model, using Node.js. Okay, So here we have publisher who sends messages in some topics, like cookery show could be some topic. And those people who are interested in cookery show will be subscribed to it and get all the services out of it. And similarly, we have a topic B, like some mechanical, some automobile channel. Okay, one cookery channel, one automobile channel. Those people who are interested in cookery channel will be subscribed to it. Some subscribers who are interested only in automotive kind of applications will be subscribed to topic B, right? The same thing. So this is all facilitated. So broker will be the facilitator for that. You cannot have a direct subscriber may not be knowing. So in one sense, I can say that we cannot in YouTube and all we can know who is a subscriber, how many subscribers I am having, and who is the provider. We know that. But in a public subscribe model of MQTT, subscribers are purely unaware about who are the publishers, and the vice versa. Publishers don't know who are all subscribed to the topics. It's all with the help of AWS, like the intermediary broker who is managing all these things. And this is another important slide where people have to think about what is the level of IoT that they are building. Okay, so here people, usually in academy, I understand that many of you are academic people. So you may be knowing that from second year onwards, people participate in different hackathons. Now Smart India Hackathon is happening and all. So usually they start with the normal Raspberry Pi, the Arduino, kind of thing with some normal, temperature sensor, pressure sensors and all. Only one single sensor is there. For example, temperature sensor, getting some data from the environment and displaying it on a mobile application. That's it. So such kind of applications, we can say it's an IoT level 1. There's nothing new in it, only some, one monitoring node. Here it's showing monitoring node, one sensing node, for example, temperature sensor, sensing temperature data. Then this data will be, displayed in your mobile application. That's it. So we can say that there is no interaction happening between cloud and all. Nothing is there. So it's all about IoT level 1. Only one single sensor, local monitoring, local processing. No interaction with the cloud. But when we move from IoT level 1 to IoT level 2, you can see that more interactions are coming. Here, there is nothing on the cloud side, IoT level 1. But in IoT level 2, you can see that there's a database coming in. There is an application. There is some communication models, WebSocket communication, RESTful communication services are there. And there is close interactions, happening between the node, the monitoring sensing node with the cloud storage. But again, a one step ahead of IoT level 1. Okay. Some interactions happening with the cloud. Then IoT level 3, what differences you can see? But here I think, I think both of them are, okay. So here, here the node itself is analyzing the data. IoT level 2, the node itself is analyzing the data and they're using cloud just for storage. But in the case of IoT level 3, you can see that sensing node, we are not actually overburdening the sensing node because it is a very miniature device. We cannot do massive AI algorithm modeling and running this model, etc. in the sensing node. So for that, if you want to have a bigger, some kind of algorithm to run, you need to run that in cloud itself, not in the edge device. So for that, it will be forwarding the data to the cloud, and the cloud will be first storing the data and go for some analysis. That is IoT level number 3. IoT level 4 means we can see multiple nodes coming in. Here and all, you can take temperature nodes. Imagine here we are having a temperature with some, some gas sensors, for example. Okay, multiple sensors are coming in from IoT level 4, so that there is some observer node also, some kind of controlling node, controlling monitoring node that can understand what is been monitoring and they can give some feedback back. Okay, like some threshold kind of thing, etc. Like opening a valve depending upon the moisture level in an agricultural land. irrigation, smart irrigation, etc., comes under this IoT 4. You can increase it with a more number of sensing elements and all. So here, when we reach at IoT level 5, you can see that it's not about nodes alone. These nodes are acting as routers as well. This becomes a more closely connected network, not independent nodes. Okay, so nodes, routers, nodes behaving as routers as well. And we have a sync node here, or we can say that coordinator. I hope you can see this. I'm actually rotating my mouse over there. Coordinator. So this coordinator, like a sync node, aggregator node, collecting all the kind of temperature data with the pressure data, vibration data, other auditory data, etc., etc. Then aggregating it and forwarding into cloud for analysis. But here also you can see that different end devices are there and different controllers are there, right, in this part. And when we move on to IoT level 6, again, it becomes multiple monitoring. That is, size is big. Like the size is actually, moving like anything. Like more number of nodes are coming in, more controlling nodes are there, and intelligent algorithms are coming in and do the analysis in the cloud. This is IoT level 6. Okay, like if you're building a smart city, you know that like your smart transportation is a part of smart city, right? Your air quality monitoring, all those things are part of smart city. Factory, there are part of smart city. Your healthcare, hospitals, IT, that is technology enabled hospitals, personal health record systems, etc. are part of a smart city. Smart education. So all these things you can think about IoT level 6. Okay, a bigger network, different sectors coming together, a part of IoT. Okay, I hope I'm making some sense now. If anything is lagging or if you are not understanding something, you please let me know. I'm not seeing any chat window right now. I'm only seeing the slide. Okay, so if you want to ask anything, you can unmute your mic and say, or otherwise we will answer it during the end of the session. I hope the time is now 8:30, right? Okay.
Yes,
I
sir.
move on. Yes, anything to be asked?
No, sir, it's going fine, sir.
Okay, thank you. So next is the data analytics part. So I'm just covering up the different parts of how actually someone like me is building an IoT. Okay, depending upon the user need and all. So first you need to have an understanding about sensors and all those things. Then communication capabilities. Then we move for data analytics. So here this actually maps with the agenda of our FDP, that is AI, right? So data analytics, that when we want to convert these raw data into some actionable outcomes, we need to do some kind of analysis. This analysis can be done either in cloud or in edge or in fog. So we have different levels of pillars of storage available. One pillar is very much close to the data generation side, that we call it as edge node or edge processing, edge storage. So many of the applications, many of the researchers nowadays are happening in the edge side only, not on the cloud. So it's all about edge computing, edge-centric networks, edge-centric communication networks. Because we do not want to wait for a longer time to get a feedback and all, because all kind of applications are 5G, 6G assisted nowadays. So those communication, we need to have things to be happen in a fraction second, in split fraction second. So edge-centric networks are there. So data analysis is the process of examining such kind of data sets in order to draw conclusions out of it, so that you will be doing a lot of analysis. That you can think about, okay, I will say something about statistics as well. About different levels of analysis. Like the first one is descriptive analysis. Descriptive in the sense, you're describing your data at the granular level. You should say about, where the data comes from, whether the data source is authentic or not, whether it is structured or unstructured, whether, all those things. So how you are describing the data and describe the data, usually in the form of some kind of charts, histograms, pie charts, etc. That is the first part. Then we go for predictive analysis, right? After describing, so so how you do that describe, you need to have some historical data with you, right? Historical data, then you will be comparing all these things and finding out some ideas and representing it in the form of intelligent dashboards or in some kind of chart, pie charts, line graphs, etc., etc. Then we go for predictive analysis. Predictive analysis in the sense we need to know, like, you are finding some reasons, like, why it had happened and what could happen next. So you're going for some prediction. So there comes, we go for some optimizations, etc. We go for some optimizations, right? Depending upon the training data, and then we go for some optimizations in that predictive analysis. Then we found out, okay, something has been found out, and what is the precautionary measures? Prescriptive analysis. So we have different analysis here, and also that again we can go for univariate analysis, bivariate analysis, multivariate analysis, and all. Okay. Before that, you'll be doing that sampling, random sampling, and all those kind of sampling, probabilistic sampling and non-probabilistic sampling, etc. All these stuffs are there. These are all part of your data analytics, your regression, correlation, even some maths people are there. You can know that you are developing some kind of hypothesis out of it, null hypothesis, alternate hypothesis. You will be doing some kind of experimental testing, that chi-square test or student t-test or z-test, etc. To make a comparison between your null hypothesis and alternate hypothesis. And again, you go for something like if time series modeling and all, you go for ARIMA, ANOVA, etc. That is autoregressive, integrated moving average models. You go for ANOVA, etc. All these parts, everything is actually coming under this data analytics. So that's why here they have put together like scientific models, theories, hypotheses, etc. Even that our the normal Google that Excel sheet, our Excel sheet, Microsoft Excel, itself spreadsheet is as an analytical tool. I can say that spreadsheet is a poor man's analytical tool. With minimal programming knowledge and all, we can do different kinds of analysis. What if analysis, scenario analysis, goal-seeking analysis, sensitivity analysis, etc. These are all things applicable for IoT. If you want to have a good understanding about these things, you go to Lufthansa Airlines website and see how AI IoT is enabling Lufthansa. And the same thing is applicable for our Indian air service provider, our own Indigo Airlines. This is how Indigo is actually running that much flights nowadays, all because of there is an influence of AI, there is an influence of IoT, where even a single airplane itself consists of thousands of sensing elements, including your radar and all the other things. Okay. So this is all about data analysis, like converting all these data sets, etc. You can apply different models for that, theories, hypotheses, etc. So that you can convert all these raw data into some kind of intelligent outcomes. So for that, we are using different architectures. Cloud architecture is there, fog is there, edge is there. Edge, that all the devices which are very much near to the user side, right? Your watches, you can see smart watches, even your table lamps, your smart taps, water taps, then your computers, many things. These are all, devices working in our operating space, the personal operating space. Then fog nodes, that is intermediate nodes. So edge devices, billions of devices are using edge infrastructure. Millions of devices are using fog infrastructure. Fog means extending the capability of cloud to a little bit longer, but not just very much near to the data generating devices side. So edge is something very much near to the data generation. Fog is not exactly at the data generation side, but away from the cloud, but not at reach of the edge. Fog. And we have cloud, thousands of cloud computing architectures are there, right? Even medical data and all, not for operations, I'm saying, because you know that edge devices, as I said earlier, these are all miniature devices. They cannot perform all the AI enabled tasks in these devices. You know that how much this watch can process, right? Minimal data, minimal models is there. So I'm not saying edge or fog is a replacement to the cloud. It is not at all replacement. It is actually, in order to reduce the burdening that, overburdening of the cloud, we are extending the capabilities, and also like certain applications need speed. For that, we are extending capabilities. That's why. And also, that we are all using this fitness trackers and all nowadays. And do you feel that every time our health data, even nowadays, I'm seeing that everyone is uploading their photos, etc., in our chat GPT, that Gemini platforms and all, we without knowing the security issues. But here, that in edge computing itself, that is the kind of data sovereignty that it is preserved. People will become more safer when the data is being generated, processed at their nearest level. That's why edge computing is more preferred for sensitive data analysis, like your banking data, financial data. There are only two important data for human. One is health, one is wealth, right? Health data, wealth data. Other data are also okay, no problem. So, so that's why, we do not want to compromise, we do not want to take any risk on that. That's why all the kind of majority of your health data, your financial banking data, etc., will be processed in the local edge centers itself without migrating into some long locations. Okay. Then comes some of the expectations from the objects. Since I told you very much about device communication, intelligent devices, etc. So the intelligence should be, whenever I'm taking a device, imagine that this is a sensor. I'm having some sensing modules as well. These are all some of the devices that we have developed here. These are all 5G filters, devices, etc., which is been using in different 5G antenna applications, working about 24 gigahertz. These devices, I don't know how many of you can see this. Okay, so these devices, so imagine that this is one of the sensor devices, and these devices are capable of self-describing it. What is the meaning of that? Like devices talking to the owner, saying that, okay, this is the purpose of me. I can be used for these kinds of applications. This is my, other specific parameters. I can withstand this much temperature. I can communicate with less than this much delay. This is the processing power. If I am handling some, 10 MB of data, this much energy will be consumed. So all these are, description or the specifications available in the sensing module that itself is describing to the owner of the device. Okay, like a metadata, like an index, and also like, if the sensing node is going to shut down, for example, like in your smart home, okay, like some Wipro bulb which is being connected with your Alexa device is going to shut down in the next 5 minutes. Then that Wipro device is giving an intimation to the owner's mobile app saying that, okay, my power is less. I'm going to shut down in the next 5 minutes. Okay. Then it could be a self-describing kind of a capability, context aware. It can understand the health status by itself and can give some kind of intimation to the owner saying that, okay, this is my capability and this is the health status And this is the, or sometimes your car is telling you, your private car, your personal car is telling you, okay, Rakesh, you please go and service me in the next 10 days. I'm having these much issues. Some engine issues are there. This is all, a part of self-describing capabilities of sensing modules. Okay, dynamic characteristics and sharing with others as well. In vehicle-to-vehicle communication, what is happening? In V2V and all, sharing resources. Like, if my car is identifying a traffic ahead, I can communicate to someone who is traveling from Ernakulam to Kottayam, saying that you can please choose the route via Ramapuram and not the other way around, that Muvatupuzha. Like I have usually come from Kaladi to, here to IT through that. Forgot its name and all. Okay, that the inner parts of Muvatupuzha. But you can take the MC road as well. So if my car is intimating the other one, in a network saying like this is an accident, there is an accident happen, or there is a road work going on, you need to take a diversion. This is again a part of dynamic characteristic of your sensing node, which is a part of your automobile vehicle. So in different scale, you can think about this. It could be a small bulb intimating a health status to the owner's mobile app, or it could be a vehicular ad hoc network setup where mobile vehicles are intimating about road accidents, road diversions, etc., to other users who are way away, away from their proximity. Okay, so these are all. So these are the expectations of different kinds of object systems, etc., which is a part of this IoT CPS network. So on the right-hand side, you can see one self-describing air, water, soil. This is the same. Actually, I copied from some of the e-commerce website like Amazon. I don't remember which site is that, but I think robo.in. I think robo.in kind of website. You can see that self-describing water, soil, temperature sensor, etc. Okay, so that it automatically communicate the configuration. So no need of, if you are non-techie people, you do not want to worry about how to program that particular device and all. It can itself, configuration, self-configuration is possible. It can communicate with the nearby similar kind of sensors as well. Okay, so this is one of the context-aware self-describing capability expected from different objects who are becoming a part of IoT CPS network. Then, once we have all these things, data processing, data storage, communication, etc., then we need to visualize it, right? We need to visualize it. So now, in my lab, DroneX lab, we are actually having a lot of projects happening between UK and India under UK IERI MIGHTY funding, as well as in EPSRC funding, and many other fundings are there. And also like IIT Kanpur, one project is going on in multi-security UAV project. So some interns are working now. They're using a gazebo kind of platform for that. Gazebo because in order to visualize certain things, the data which has been captured by drone, we are actually providing a support for the Kerala police, how to monitor the crowd management in mass crowd places like Attugal, Pongala, Shabarimala, and similar other kind of community-based or that religious-based festivals happening in Kerala, or it could be a political meeting as well. So this is a request came from Kerala government. They are buying drones from outside. They're asking us to provide some edge-centric drones, which can provide an exact number of humans, like dividing how many females, how many males, how many children, whether the flow is on the right direction or not. Anomalies are detected, and need to create a digital framework, etc. For that, we need to visualize it. So similarly, in different IoT setup, we are using, even you can think about your Ola car, Ola, or your Uber, even Swiggy, Zomato platforms. They're all using such kind of tools. Even Burger King kind of platform, they're all using this kind of Grafana or Kibana, Power BI, Microsoft Power BI, etc. for analysis, real-time analysis, and Even I just mentioned you about the Lufthansa Airlines. You can see that Lufthansa, which kind of visualization tool they are using. These are all, add-on services to optimize their processes, to optimize their airplane operations and all. Even the same thing is applicable for great airports like, that Changi Airport in Singapore, as well as our Heathrow Airport in London, biggest airport, right? So there are all you can find such kind of a Power BI and these kind of tools, visualizations, and can give you, that query analysis, different kinds of supports are there, Elasticsearch support, etc. are there. Okay, so some visualization tools, and even many of the small things, we are actually buying credits from Amazon Web Services and using it. Many of us are using it, right? Even developers, academicians like me, for my research purpose, and now we are using AWS credit analysis. Okay, so these are all, some idea about the different tools and, the AWS insights and all those things related to IoT. Now moving on to the communication technologies. Somewhat pressure around 8:50 now. Okay, so here the next thing is 5G. So 5G, that this was I will not tell, this is the current talk of the town. Some time ago, it was the, huge high topic, the burning topic of the town. Even IIIT in 2022, we applied for a 5G license. We got some boards from a German company. We were having some projects on 5G test bed and analysis and all, especially on ultra reliable low latency communication. So here 5G NR, it needs to satisfy three important pillars. NR means new radio. Okay, 5G new radio. So here, why I am putting 5G here? Because we need a strong communication facilitator to make things automate, right? Otherwise, we cannot imagine such kind of automation. So that's why 5G comes in place here, and it becomes 5G enabled IoT networks. Okay, 5G IoT. So 5G new radio, we have three important areas of research, or the three areas of interest. One thing is the massive Internet of Things. I told you about the different devices coming from different sectors for connectivity, which we call it as massive. Massive means a huge number. Then enhanced mobile broadband. We talk about broadband. This is all about the enhanced EMBB, means enhanced mobile broadband. EMBB. It is like using a normal mobile phone. Can we take a 4K video and transmit lively? That is enhanced mobile broadband. And we have mission critical control. What is that? Strong security, ultra high reliability, like, the lost, you can see here, less than 1 out of 100 million packets lost. So that the accuracy will be 99.99999%. And ultra low latency as long as 1 millisecond. That is, you can download, 10 cinemas of 4K quality in 1 millisecond. But, we are not using 5G in this fashion now. We are using the true 5G given by our, Reliance as well as Airtel and all. It is not the real 5G. The real 5G is all about, the conditions which have been written over this slide. And about the connectivity, ultra high density, like 1 million nodes per kilometer. No one will say like, I don't have coverage. Okay. For that, we'll be using multiple input, multiple output antennas, MIMO antennas for every per kilometer. So it should be closely densed. Some other issues are there, like interference issues, co-channel interference issues, etc. will come. But again, it depends upon the, meet the demands of the user or giving a user enriching experience on calling, on data, as well as on viewing like videos and all. Okay. So these are all like, the vision of 5G, I could say. Now itself, even though we didn't complete we didn't explore the full potential of 5G, but we are in a rush towards reaching 6G. Can anyone tell me, I need to take a 1 minute break. Can anyone tell me what is the fundamental difference between, 5G, 6G with the previous networks? First generation to fourth generation, we have 1G, 2G, 3G, 4G and all. And 5G and 6G, we are treating separately. Why? Like our AI. Even though we have artificial neural networks during my BTech period itself, but we are now actually, looking more into AI related stuff, depending upon different kinds of use cases. So what would be the fundamental difference between the previous generation networks with 5G? You need to unmute, otherwise I cannot hear. I cannot see. Any idea? Anything? The previous first generation to fourth generation, what was the, who were the generators? Generators means data generators. Human, right? But 5G onwards, 5G and beyond networks, it's not for human. We are just a part of that network. 5G is not built for human-to-human communication. It is built for device-to-device communication. So that's why 5G, AI, IoT, etc., these terminologies or these technologies are tightly intervened with our usual, life. This is assumed to be a life fabric, like our electricity. Now, electricity is everywhere, right? Electricity is everywhere. We can use it for different applications. But you cannot see electricity like AI. We are not seeing AI, right? We are experiencing it. Similarly, AI, 5G, and all these things we are experiencing, not actually seeing with our eyes. Okay, so 5G, 6G, etc. are just like a backbone kind of network. We can plug it, your application, and use it. Okay, you can use smart home application, you get the service. You need smart healthcare, you get the service, but the user demands are different. The application demands are different. For that, that's why now onwards, we are not depending upon a hardware approach. We are going for a software-defined approach. That's why, we have cognitive radios, software-defined radios and all, by which we are actually dividing the network logically, right? Like our ISO, OSI, and all, we are actually dividing logically, right? Similarly, here also logical divisioning is there. We call it as network virtualization, okay, etc. in 5G, like, dividing network into different logical layers, every layer meeting different user demands. Okay. Yeah. So these are the three-tier spectrum usage for 5G, starting with the low band, mid band, and millimeter wave. So millimeter wave, that's why, we have millimeter wave is nothing but, the size of the wave will be in the form of millimeters. It can travel up to some 5 millimeters and all. So here, the capacity, like we have above 24 gigahertz, we have 6 gigahertz to 24 gigahertz. We have frequencies spectrum below 6 gigahertz. That's why we have low band, mid band, and that high band frequencies. So mid band means wide coverage, greater capacity between 6 gigahertz and 24 gigahertz. And here 24 gigahertz to 88 gigahertz, or theoretically speaking 100 gigahertz. And here it will be below 6 gigahertz, low band. So like the board that we are having here in Reply is only low band, not in the mid band, because we bought it during the discussions of 5G. That time, that complete architecture was not available. Then these are transformation elements. So everywhere you can see the influence of AI/ML. So AI/ML is not at all a separate element. Now, those people who are interested in AI-driven communication, this is a space. There are a lot of open research challenges available in 5G, 6G area. You can choose one application. So whenever you are applying for certain funding and all, you need to apply, you need to understand what is the use case. Theoretical studies are not supporting by Government of India nowadays. No theoretical work. You need to convert everything into some kind of product. Enough, Modi government is saying like, enough and more publications are there. People are working on the same area and one area, multiple publications. Like from the day by which he completed his PhD, now also the same area he is continuing. So, it is not as easy like to convert idea into product. So that's why we are having a lot of innovation hubs in place, which can convert all the innovative ideas into market. So whenever you are writing a product proposal, you need to specify what is the current technology readiness level of your product. It is level TR level 3 or 4, and you need to submit a TR level 6 or 7 at least. So this is the way by which that research projects, the ANRF and all those things are working nowadays. That's why many of the projects are not get recommended, because the clear deliverables have not been showcased. Okay, I will do it in a separate seminar, not now. But again, so this is the massive MIMO technique. Massive MIMO. Now we are actually moving from 5G to 6G. It becomes reconfigurable intelligence services. Reconfigurable intelligence services, RIS. Okay. Then IoT capabilities are the virtualization concept, software-defined networking, network slicing, logically slicing network into different layers, and each layer meeting a different user demand. Then network densification, like everywhere you can see that nowadays something known as holographic surfaces. The signals will be reflected everywhere, so that no one will be facing issues like cell drag and not getting signal and all. Everywhere will be getting signal because of the two important principles coming in 6G. That is the reconfigurable intelligence surfaces as well as holographic surfaces. Okay. Then moving on. So the 5G solutions are nothing but the URLLC, that is ultra reliable low latency communication, smart city communication, smart home applications and all. So ultra reliable low latency means like 0.0001 second. So many open research areas are there. You can work on. One area I can tell you is AI-driven URLCC applications on drone, or you can see underwater communications, where GPS is denied, GPS-denied environments. Or even you can go for oceanographic studies. Even go for, nowadays DRDO has been called for some, project calls are there. There also you can apply 5G assisted URLCC. And the same thing you can be, you can simulate using MATLAB or, in Python, URLCC and all. Simulation can be done. But if you want to go for a real-time implementation, you need to, like, for example, in my case, I'm buying drones, not buying, actually building drones with the components and all. Some microcontrollers you can buy. Basically, I will suggest you to buy, that Jetson Nano kind of thing. At least Raspberry Pi and all now won't work in real world experiments. So there are all, you can use some kind of 5G test boards as well, like for providing such kind of ultra reliable low latency communications. So this is a kind of unified intelligent transportation mechanisms where you can see like many communications are possible. V2V, V2I, V2P and all. It is vehicle to vehicle communication, vehicle to infrastructure, vehicle to pedestrian communication, etc. This is no more a sci-fi movie or a kind of a fiction. This is a real world implementations available in many roads. You can find the road between Paris and France. Okay, you can look into the website known as Highway England. Highway England website, you can see such kind of infrastructures. Even you can see in Australia, you can see, that your car company named Lexus, they have already experimented, even Audi, they have experimented V2V, V2 and V2P in Australian roads. And the same thing is applicable for Denmark and Norway. They're also, these are the places where we have excellent road transportation facilities, implementing at least V2P and V2I. Okay. And this is the way by which we are actually moving in self-driving cars and CV2X, cellular vehicle to everything. Vehicle to everything means vehicle to X can be replaced by V, that is I to V or V to P, and etc. All those things. And we have a roadside unit. Your intelligent cameras will guide you accordingly whenever some pedestrians are crossing the road or something, like some road accidents, as I mentioned earlier. Hazardous warning and all those things. Okay, I'm skipping some of the slides. So here, there is a great influence of VR, AR technology also. Like whenever you can go to Kerala Police Cyberdome website, where we have implemented a metaverse environment there, where you're using this VR, AR, etc. technology there along with the IoT sensors. Okay, you can see the virtual environment which has been created in Cyberdome website. Go to Cyberdome. There you can see virtual environment where clearly written by IIIT Kottayam, Gyan Innovation Lab. So these technologies have a close connection with our, anyway, this is a user enriching experiences, immersive experiences. So in order to make some digital environment, closely connected with physical, we need to go for virtual reality, augmented reality, extended reality, etc. Sometimes in close synchronization, audio, video could be closely synchronized. Or if you want to augment the physical environment, we can go for this mixed reality kind of thing. Okay, so these are all technologies associated with this IoT CPS with AI. Then intention sharing, autonomous driving. Even there is one area that you can research is vehicle platooning. Vehicle platooning is an area where it is actually a connected truck technology, technology where a leader will be there, followers are there. So only one driver will be there in the leader, others will be following in the highways. It is not it cannot be applicable to Indian roads. Some developed roads you can see such kind of vehicle platooning things. Okay. And so that the new real world reality is cyber physical, where we have people as data consumers and generators. We have business technology in place. We have assets, things in place. So there is a close connection between physical and different software elements. And then, okay, evolution. So here you can see that, these are the major 6G technologies that you need to look at. That is wireless with artificial intelligence, with Internet of Everything. You have mobile intelligence. You have different key use cases like holographic communications. That holography means, that signals coming from multiple directions, okay, coming from multiple walls, buildings and all. It can create a 3D image. That is a holographic communication, right? 3D image. So like a teletransportation kind of thing. So holographic communication, digital twin, autonomous mobility, extended reality, smart healthcare. These are all some of the use cases of 6G. And the spectrum also you can see here, we are using multi-transmission technology, like we are having NOMA. NOMA means non-orthogonal multiple access. We have modulation, correlation, multi-wave technology, etc., which are all part of 6G. What is the fundamental difference between 5G and 6G? Because 6G is highly mobile. Because all the transmitters and receivers are moving, so that there is a problem known as a delay spread problem. Delay Doppler spread problem. Delay Doppler spread problem is there. So in order to do that, in order to cope up with such kind of wireless issues in 6G, you need to go for techniques like NOMA, non-orthogonal multiple access, which is again a new technology, because previous technologies we were using was OFDMA, orthogonal frequency division multiple access kind of thing. But here nowadays we are using NOMA, where everyone can send their signals on the same frequency, on the same time, but they are separated by their power, energy power. Okay, that is norma. And we have intelligence. So whenever we are discussing about 6G, you should understand that AI is a native of 6G. So like without AI, we cannot establish a 6G communication network. So the AI is at the core. So that's why intelligence is there at the core, at the edge, at the air. So that's why we are actually connecting terrestrial networks with the non-terrestrial networks, integrating land, space, and air. Sorry, integrating underwater, land, and air. There is a terrestrial, non-terrestrial connections. Communications are the these are all the vision of 6G. Okay, and where we cannot remove AI/ML. AI/ML is at the core, at the edge, as well as at the air. AI interfacing, air interfacing for taking deterministic, non-deterministic kind of decisions. Like if drone is moving without any human intervention, like in war scenarios and all, whether I want to throw a shell on that certain location or not, the drone has to take its own decisions. This is a kind of AI capability. Like you need to understand what is the object. So image vision will be there, object will be there, analysis and taking the right action at the right point of time without waiting for a command from the human side. Okay, so these things will be more achievable with the help of 6G. And this is a kind of new area you can look into if you're interested in wireless communication. This ISAC area, that is integrated sensing and action, like integrated sensing and communication. That is, nowadays you know that if you want to communicate, you have a sensing element, separate hardware should be there, and for communication, separate hardware should be there. Think about whenever you are sending a wave, that wave itself can sense, that wave itself can communicate. So clubbing, sensing, and communication into one single element. That is known as ISAC equipments and all. So there you can find, this is how we are actually making a, integration between space, air, and the ground sea networks. Actually need some more time, I think. So it's 9:10 already, but okay. So this is the idea. Then, okay, more slides are there. Okay, so anything to be asked now? So I'll wind up somewhere because it need more time to complete. So I hope I have given you some idea about those 6G, 5G setups, IoT, cyber physical systems and all. So some research directions also I can give you. Yes. So these are some of the research directions you can work on if you're really interested in wireless communication. Like you can think about, since my prime research nowadays going on a non-orthogonal multiple access, artificial noise injection, how to avoid security problems like jitter, jamming, all those things in the physical layer, in the MAC layer, as well as application layer. So application layer, I'm using, encryption strategies like, not encryption, security primitives like blockchain security I'm using, and I'm using that one attribute-based encryption, ABE. Attribute-based encryption is a flexible kind of, encryption technology, which is far better than the conventional symmetrical or public key cryptography techniques. So I'm using ABE. ABE is a right candidate for such kind of application, especially I'm doing it on a drone side. Then we have, you can work on sub-terahertz communication, millimeter wave communication, etc. Especially like how to design, these kind of things. Like this is something on a substrate integrated waveguide, SIW antennas. Again, you can make it AI defined because like you can connect this into any kind of your software, and you can control the channel modeling. You can control the that signal penetration, channel modeling, etc. No, that's why everything is cyber physical. This is a physical thing. You can control this element with some your software things. Okay, then AI ML for network optimization. Like I told you, like beam direction. Beam means signal beams, resource allocation, then mobility. All those things can be controlled using AI ML. Then some other security primitives you can see here. People are working on a role-based access control, RBAC. That is predefined, like role-based means professors could be a role, associate professor, lecturer, researcher, all those things are role-based access control. Attribute-based access control means what? Again, I can redefine the attributes like professor with 15 years of experience or assistant professor who have joined recently. Like that, attribute-based access control can be given. Policy-based access control, capability-based access control. These are all, different kind of authentication, encryption primitives, which has been using in IoT assisted technologies. Even nowadays, the most preferred one is a lightweight cryptography-based access control because these edge elements do not have the power to withstand, the other kind of homomorphic crypto systems or these kinds of algorithms. So that's the most preferred one is a lightweight cryptographic algorithms. You can make your advanced encryption standard AES lightweight kind of thing. Lightweight AES is also there. So the current challenges, so those people who are interested in security side, you can work on the secure communication. For my use case, I'm doing drone-to-drone communication, drone-to-ground communication, how to make it secure. For that, I'm using Cha-Cha-20 kind of algorithms, Cha-Cha-20 kind of algorithms, which is found to be a very good algorithm, which can work between drone-to-drone, especially in a MAC layer communication. Okay. Otherwise, I'll be going for, in order to protect the logs and all, I'm using blockchain. And to provide a better access control to your server, I'm using different attribute-based encryption mechanisms like cyber physical CPAB, ciphertext policy attribute-based encryption, and key policy attribute-based encryption. So these are some of the encryption algorithms that we can use. I do understand that with 1 second and all, you may not be understanding all these things, but I'm just providing you some names so that you can sometime after this talk also you can Google it and find out one of the applications. So what I have told is attribute-based encryption, role-based access control, then lightweight-based cryptographic algorithms, then cipher policy attribute-based encryption, key policy attribute-based encryption, right? So and different design parameters. I don't know how many of you are interested in hardware and all. Then you can think about the storage sizes, IoT sensors, and all those things. Okay, so I will provide this slide. Actually, I have already provided this slide to the coordinators of this workshop. This FDP. I'm sorry that I couldn't complete the 74 because there are many concepts comes in between. So it's hard to complete because it's all about my mismanagement of time. I do understand that, but I think I spent some time more on some other aspects. But I think I have somewhat give you some idea about all these things because in FDPs and all this is the maximum. Like one can provide some overview. Otherwise, I can provide you my work. There is no. I do understand that some people will provide their own research works in FDPs. I'm against that because why? Because since I am working on drones and all, and sometimes many of you may not be that much interested in one particular area of research. So why unnecessarily I'm wasting your time by going through the findings that I have gained through my experience. So it's easy for me to make you understand, but you may not. So this is a kind of an overview about IoT, CPS, and what all things that you can look at as a part of your research and as a part of your academics. So these are some of the research areas I'm currently focusing on. This was actually described by the during the introduction. During the introduction, they have described some of my research areas of focus and some of the areas that currently working on some real world projects and fundings and all those things have been written over here. So you can connect with me if you are interested to collaborate. Please do connect with me. This is my profile. I'm using this number for the last 25 years. this 9447539622. It will never change. You can WhatsApp me, you can email me, you can contact through my official webpage as well. So with that, I am concluding. Thank you so much for patient hearing. I do understand that this could not be a digestive session because you are hearing an FDP continuously from 5:45 p.m. onwards. Even no one can listen, 5:45 to 9:17. Now it's 9:17 on my watch. So, but thank you for the opportunity for all the organizers of this FDP from Narmada College. I wish to collaborate with all of you. If anything is, this is like a mutual win-win situation. It's not about tech and non-tech. Anywhere we can collaborate. There are enough and more funding platforms, such kind of avenues are available. I'm always open to that. Thank you so much. Those people who have listened carefully, who have some interest in this kind of work, please do ask certain questions if you have.
Thank you, sir. Thank you for the wonderful session. Participants, if you have any query, please unmute yourself or message through chat box.
So,
No feedbacks or no comments other, I think. No, I do understand that because even if I'm sitting as an audience side, from 5:45 p.m. onwards, I may be looking at some of the, this is precious to me. These slides, these presentations, these works are precious to me. I don't know how much I can convey to the audience at this point of time. So, but if you wish to collaborate, if you could understand some of the things I have narrated through the presentations, please do collaborate.
Sir, one not a query actually.
Okay.
If our students in Narmada College, if they do want to convert their project into an IoT based one, how could we what can a IIIT can provide?
Yeah,
to
the IIIT, I told you, right? In my lab, I can, because this is people will be having different interest and all. So in my case, I can tell you, my labs are open to, everyone. I have two different labs here, one focusing entirely on drone applications. The other one is based on embedded systems and IoT. So we are usually converting all the student ideas, faculty ideas, etc., to the market. So, we have some, this is all because of a teamwork. This is not like I'm just, following, leading all these activities. We do have wonderful teammates here in IIIT, or they're having positions like Chief Innovation Officer, Mr. Anirudh. He is actually the key enabler of such a lab, connecting with the different groups, getting grants and all. I'm also having a different area, different approach towards the lab, getting grants from outside India, making the lab actually, outside the walls of IIIT, getting more connections from foreigners, foreign collaborations and all. So this is not we are not making money, personally speaking, I'm not making any money out of it. This is all because of the interest and passion. This is actually overburdening as well, since I am now wearing the same shirt I was wearing from 5:30 a.m. onward. I'm still in my office in IIIT. I haven't gone to my home also. So this is all because of the passion and work, and we are actually sacrificing our personal life as well. But I do understand this is at some point of time, it may not be. Now I am 41. So I don't much feel proud about all these things, because there are many things to be taken care of apart from career. But somehow, I am into this, because many of the people here, they are still in these labs and all, up till 12 or 12, and even PhD scholars. This is not about, someone is asking us to be in the lab and all, but many of us actually want to, since we are into such an institution, we need to prove sometimes ourselves. Okay. Otherwise, the next day register or director will be asking, Rakesh, what were you doing last 1 month? Okay. The normal teaching and learning process, which happens everywhere.
Yes,
So,
that I could understand. That is when we asked for a session, you were very happy and very ready to accept for that. Even I don't know you personally. So you were so
no,
happy.
the main problem with me is actually I'm traveling around some 140 kilometers per day.
Yeah,
70 kilometers from Kaladi area to Pala and again going back.
yeah. Yes, sir.
Okay,
Thank
okay,
you.
okay. This is away from the technical part again.
Thank you, sir. Thank you for
Okay.
sister.
So anytime you can contact me, no issues. So I have the number of Liji madam and Sherry, right? No, Sherry ma'am also as well. I think, but I haven't saved.
Sir, you will be having Sharon sir's number, Sharon Matthew, I think.
Sherry Matthew,
Yeah,
right?
yes,
Okay,
sir.
okay. Okay.
Yes, sir. And so we have the PPT also that you have shared. So we'll
Yes,
be
yes.
sharing it to all the
Yeah, please
participants.
do share with the other, interested participants.
Yes, sir. Sure. We'll share it in the drive for the participants. Liji,
Okay.
could you?
Yeah, ma'am. My heartfelt thank you to Rajesh sir for such a wonderful session. On behalf of the Department of Computer Science, Namla College.
I don't know, since this is mainly like a cross layer kind of a subject, it is, if someone asks you, is a CSC subject? No, it's not a CSC. It's neither ECE nowadays. It's like ECE plus
Yeah.
CSC subject. So those people who are having some idea about this wireless and all, then only can understand the things. Otherwise, it will be like a kind of, rockets going above your head.
No, though the session was a bit technical, it was understandable, sir.
Okay.
We could understand it, yes. So thank you so much for your
Okay,
session.
thank you so much. Thank you for this opportunity.
Thank you for all the participants.
Yeah, thank you.
Thank you.
Thank
Have a
you.
good day.
Sir, normally we say it's a food for thought, but this was more than a food for thought. So thank you. Participants, kindly remember to fill up the feedback form that is given in the chat as well as in the WhatsApp group. So good night. Have a peaceful night and see you all tomorrow at 6 p.m. Thank you so much. Thank you.